What if everything you've ever believed about reality is just the surface layer? Right now, even as you breathe, your body is obeying laws that bend time, curve space, and let particles be in two places at once. This isn't science fiction. This is physics. Real, proved, mind-bending. And you're about to fall asleep, right in the middle of it. Comment where you're watching from, and tell me what's the one science fact that blew your mind the first time you heard it. That the universe has given rise to creatures who look back at it and ask why. Even now, those questions continue. In the pulse of your chest, the rhythm of waves, the hum of electricity through a wire, the story unfolds, not loudly, not quickly, but always. Because science doesn't sleep. It just gets quieter, more subtle, more curious. And so the questions deepen, and with each new breath, the next layer of the universe begins to reveal itself. Let's keep going. Imagine peeling away the world, not in a violent way, but gently layer by layer, like turning the pages of a book you never knew was written. At first, you see trees, clouds, streets, screens, ordinary things. But then, as you go deeper, you begin to sense something beneath it all. Something steady, something precise, a hidden structure, guiding everything. That structure is what science explores. Not just facts or data, but the invisible scaffolding that holds the universe together, the patterns that repeat, the rules that never change, the quiet logic behind every leaf, every star, every breath. And as you listen now, in this quiet moment between the noise of life and the stillness of rest, let that thought settle into you, that everything around you follows a language more ancient than words, more constant than time, a language written not in ink, but in motion, in energy, in form. Let's begin with something simple, a falling apple. To most, it's just a moment. But to Isaac Newton, it was a key that unlocked a truth so universal, it applied not just to apples, but to planets. Newton realized that gravity was not limited to Earth. It reached out, endlessly, between all objects with mass. The more massive they are, the stronger the pull. The farther apart, the weaker it becomes. But it never disappears, not completely. He wrote it as a law, a description so elegant it fit the moon and the tides in the same sentence. Gravity is why your feet stay grounded, why the oceans rise and fall, why the Earth orbits the sun with predictable grace. But what's fascinating isn't just that gravity exists, it's how perfectly it works. Drop a feather and a bowling ball on the moon, where there's no air, and they hit the ground at the same time. Why? Because gravity doesn't care about shape or texture. It's impartial. Only mass matters. That consistency is everywhere in science. Take light, for instance. It travels at an exact speed, roughly 300 million meters per second in a vacuum, not faster, not slower, always the same. And that speed isn't just fast, it's fundamental. It defines the structure of reality itself. Einstein didn't just notice this, he built an entire theory around it, relativity, and in doing so he changed our understanding of time. Because time, it turns out, isn't absolute. It bends. It stretches. If you move faster, time slows down for you. If you approach the speed of light, it merely stops. Not metaphorically, literally. That's been proven with atomic clocks. Put one on a fast-moving plane and compare it to one on the ground. They don't match. Time shifted, ever so slightly, but undeniably. Space does the same. A heavy object like a star bends the space around it, so when light passes near it, the path curves, not because light chooses to bend, but because space itself is curved. This bending of space and time is what we call gravity now, not a pulling force, but a warping of geometry. You're not being pulled down, you're sliding along a curve in space that leads to the Earth. It's strange, but also beautiful, because even in its complexity, the universe behaves with order. It may not be obvious, but it's there. Now zoom in not to planets or stars, but to the world beneath your skin. Atoms. Every object you touch, every breath you take, every heartbeat, all made of atoms, tiny vibrating units of energy and matter. But here's the strange part. They're mostly empty. If an atom were the size of a football stadium, the nucleus would be the size of a marble at the center. The rest? Space. But somehow, these nearly empty particles form everything you see and feel. They cling together through forces invisible to the eye, creating the illusion of solidity. And they're not static. They vibrate. They interact. They exchange energy. That's what heat is. Not a substance, but a measure of motion. The hotter something is, the faster its atoms move. Touch a hot stove, and the atoms in the metal are vibrating violently. That energy transfers to your skin, and that's heat. But there's more. Atoms aren't little balls orbiting like planets. They behave more like clouds, blurred regions where an electron might be, but you can never be completely certain. That uncertainty is part of quantum mechanics. At this level, reality isn't fixed. It's probabilistic. Particles can be in multiple states at once, only collapsing into a specific outcome when observed. It sounds impossible, but it's the foundation of modern technology. Without it, there'd be no computers, no lasers, no MRI machines. And yet we barely notice. Science hums beneath everything. Quiet, reliable, often invisible, like the programming of the world. And in this hum, patterns emerge. One of them is entropy, the tendency of systems to move toward disorder, to go from organized to chaotic, from structured to scattered. It's why your coffee cools down, why sandcastles crumble, why a broken plate doesn't unbreak. The universe favors disorder. Unless energy is used to hold things together, that's what life does. It takes in energy, uses it to maintain order, to resist entropy, temporarily. Because in the end, even life yields to it. But not without a fight. Your body is an energy system, from the food you eat, to the oxygen you breathe. It's a constant balancing act of inputs and outputs. Chemical reactions that turn sugar into fuel, heat into motion, thought into action. And in that system your brain stands as the most complex structure known to science. 86 billion neurons, each capable of forming thousands of connections, trillions of pathways. A network so vast, it exceeds the number of stars in the galaxy. And yet it runs on the same rules: electricity, chemistry, biology. The same forces that move electrons through wires also move signals through your thoughts. The line between biology and physics isn't as clear as we once thought. They are not separate disciplines. They are lenses, ways of looking at the same unfolding truth. Take photosynthesis, plants converting sunlight into sugar. It sounds simple, but it's quantum. Light particles hit a leaf, electrons jump, energy moves through a maze of molecules and transforms into matter. That's science. Taking something intangible, like light, and turning it into something solid, like a tree. Even time itself has rules. It only moves in one direction forward. Why? Because of entropy, because disorder increases, because the past is ordered and the future is yet to scatter. And through it all, we observe, we measure, we test. Not to control nature, but to understand it. The scientific method isn't just a checklist, it's a mindset, a humility before the unknown, a willingness to be wrong, to ask again, to look deeper. Even now, our best theories are still theories. We know more than ever. And yet, we still stand on a shoreline facing an ocean of what we don't know. The beauty of science isn't in its answers, but in its questions. In the courage to wonder, in the patience to observe, and in the quiet awe of realizing how much more there is to learn. That curiosity continues, not as a loud voice, but as a steady whisper beneath every falling leaf, every flicker of starlight, every breath. And so, the journey goes on. Chapter 2. Time Illusion and the Physics of Now. Time is strange. We live by it. We measure it. We age, we remember, we wait, and still, no one really knows what time is. It flows forward and never backward. But why? Why does a broken glass stay broken? Why do we remember the past, but not the future? What is it that gives time its direction? Science, this is called the arrow of time. And that arrow only seems to point one way because of entropy. A quiet but relentless drift toward disorder. In thermodynamics, entropy is the measure of how disordered a system becomes. When a hot cup of tea cools down on a table, it's not magic. It's heat energy moving from a concentrated state to a more spread out one. From order to chaos. This process never reverses. The tea doesn't get hot again on its own. Entropy always increases. And as entropy increases, time appears to move forward. So maybe time isn't flowing. Maybe it's just the story we tell ourselves as we move from low entropy to high. Some physicists suggest that time isn't even fundamental, that it's not built into the universe like space or mass. Instead, it might emerge just a convenient way of interpreting change. But if time isn't real in the way we think, then what is now? Why does the present feel so solid, while the past feels untouchable, and the future uncertain? In physics, there's no universal now. Two people in different places moving at different speeds may not even agree on what now is. This is one of the mind-bending predictions of Einstein's theory of relativity. Here's how it works. Imagine you're standing still on Earth. A clock ticks in front of you. Another person flying past you in a spaceship near the speed of light will see your clock ticking slower. To them, your time is stretched. But to you, it's normal. That isn't a glitch. It's reality. Time passes differently depending on speed and gravity. This is called time dilation. The stronger the gravitational field, the slower time passes. This isn't a theory. We've confirmed it with atomic clocks on mountains ticking slightly faster than those at sea level. Even GPS satellites have to correct for this effect, or your phone's map would be wildly off. So what does that mean for us? It means the ticking of time depends on where you are and how fast you're moving. There's no single universal clock. There's only relative time, subjective time, experience time. And what about the past and future? Are they gone, or do they still exist, waiting quietly in the fourth dimension? Some physicists argue for the block universe, a view where time is like space. The past, present and future all exist at once, like different locations on a map. In that view, you don't travel through time, you are a line through time. Your whole life, every moment, every breath, already drawn out, already existing. You just happen to be experiencing one slice of it, right now. It's an unsettling thought, but strangely comforting too, that nothing is ever really lost, only hidden in another layer of space-time. And yet, to us, time still feels real, because the brain is a storyteller, a rhythm keeper. Every second, it builds a continuous thread of memory and anticipation. Your internal clock, known as the circadian rhythm, keeps time using chemical cycles and genetic switches. It regulates your sleep, your body temperature, your alertness. And it's synced, not by your thoughts, but by light. When sunlight hits your eyes in the morning, it sends signals to your brain's suprachiasmatic nucleus. That signal resets your clock, tells your body it's time to wake. That's why jet lag hurts. Your body clock and the world clock are out of sync, and your cells don't appreciate the confusion. But even deeper than circadian rhythm is your perception of the present moment. How long is now? A second? A millisecond? Turns out your brain has a processing window of about 2 to 3 seconds. That's your now, the size of your mental present. It's just enough time to hear a phrase, to react to a sound, to register a thought. Outside of that window, everything either becomes memory or prediction. Your consciousness rides a wave of rolling present, never stopping, never repeating, never quite catching the future. That illusion of flow is just your brain doing its job, assembling snapshots into a continuous movie. And memory? That's just data compression. Your brain doesn't store everything, only the meaningful pieces, the ones that matter for survival, for identity, for emotion. Memory changes every time you recall it. Each time you remember something, you rewrite it, just slightly. You're not remembering the original moment, you're remembering your last memory of it. Which means your entire life story is being edited in real time, by you, without you noticing. Now think about dreams. The way time bends in sleep, a single moment in the real world can stretch into an hour-long dream in your mind. Why? Because your brain is free from sensory input, no longer anchored by external events. It weaves time out of imagination, a new internal clock made of stories and symbols. In that way, dreaming is a kind of time travel, a way to explore alternate timelines, emotions that never happened, conversations that were never said. But even in sleep, your brain keeps ticking. Neurons fire in rhythmic bursts. Waves of electrical activity pulse through the cortex. These waves are measurable, and they happen in distinct phases. During deep sleep, your brain enters delta wave states, slow, high-amplitude cycles that restore and regulate. During REM sleep, brain activity becomes erratic, dreamlike, similar to waking thought. And all of it follows time, not external time, but biological time, your own private clock. Even the way you count time is unique. Children experience time differently than adults. A summer at age 6 feels endless. At 40, it vanishes in a blink. This isn't just nostalgia. It's due to how the brain encodes new experiences. The more novelty you experience, the slower time seems to pass. Routine compresses time. Variety stretches it. That's why travel, love, fear, and discovery feel timeless. They slow the clock down. They break the pattern. They demand attention. Your sense of time is tied to your awareness. And awareness is fragile. Now, let's shift to the atomic level again, where time still exists, but not in the way you're used to. In quantum mechanics, the fundamental equations are time-symmetric. They don't care whether time moves forward or backward. The rules work either way. There's no preferred direction. This is a major puzzle in physics. Why does the universe behave symmetrically at the smallest scales but irreversibly at the largest? Some suggest that the universe began in a state of extremely low entropy, a cosmic reset point, and everything since has been a slide into complexity and randomness. Others propose that time is an illusion entirely, a construct emerging from quantum entanglement, or even from information flow. In that view, time isn't ticking forward, it's a tapestry, woven all at once. What we feel as time is just the way our consciousness moves across that fabric. None of these ideas are settled, but they all point to the same truth. Time is more flexible than we ever imagined, more personal, more relative, and possibly not real at all. But even if time is an illusion, it's one we live in, one we feel in every heartbeat, every memory, every moment like this one. And maybe that's enough, to know that the mystery continues, layer after layer, each answer revealing a deeper question. The clock still ticks, but now, perhaps you hear it differently. Chapter 3: The Hidden Forces That Shape Everything. There are forces around you right now that you cannot see, cannot touch, but they are shaping your body, your environment, your reality. You're held to the earth by gravity. You're prevented from sinking through your chair by electromagnetic repulsion. Every chemical in your body functions because of the strong and weak nuclear forces. These four: gravity, electromagnetism, the strong force and the weak force, are known as the fundamental interactions. They are the quiet architecture of existence. We often think of gravity as the strongest force. After all, it holds planets in orbit and pulls oceans into tides. But among the four, gravity is actually the weakest by far. If you hold a paperclip near a small magnet, the magnet wins against the entire gravitational pull of Earth. That's how weak gravity is compared to electromagnetism. It only seems dominant on large scales because it never cancels itself out. Gravity only attracts, it never repels. So while atoms and charges can balance out and neutralize, gravitational force just keeps adding up, quietly, invisibly, across billions of light years. Now, let's look at the strong nuclear force. It works only inside atomic nuclei, but it's powerful enough to overcome the intense repulsion between protons. Remember, protons are positively charged. They don't want to sit near each other. They should fly apart. But they don't, because the strong force glues them together. It binds quarks inside protons and neutrons. It's the reason matter has mass. Without it, atoms would not exist. The universe would be empty space. Then there's the weak nuclear force. It governs radioactive decay, the slow transformation of particles inside atomic nuclei. This is the engine behind nuclear reactions in stars, and the ticking heart of carbon dating. When a neutron decays into a proton, an electron and an antineutrino are released. That process is governed by the weak interaction, a force essential to life, yet too subtle to feel. So now, imagine this. You are made entirely of particles held together by these invisible laws. Your atoms are bound by the strong force. Your body interacts with the world through electromagnetism. You stand on Earth, thanks to gravity, and time flows for you partly because of decay, powered by the weak force. Every second you are alive, you are a four-force symphony, and none of it can be seen with the eye, but it's happening. Let's linger on electromagnetism for a moment, the most familiar yet most versatile of the forces. It holds electrons in orbit around nuclei. It determines the structure of atoms and molecules. It powers lightning, magnets, electricity, chemistry, even your brain. The reason your hand doesn't pass through your desk isn't because the matter is solid, It's because the electrons in your skin repel the electrons in the desk. That repulsion is electromagnetic. Even color, what you see as red, blue, green, is just the way your eyes interpret electromagnetic waves of different frequencies. Light is electromagnetic radiation, and what you see is only a tiny sliver of the full spectrum. Most of the universe is invisible to you. Ultraviolet light, X-rays, gamma rays, microwaves, radio waves, they're all around you all the time. You just lack the biological sensors to see them. But they are there, moving through walls, bouncing off satellites, warming your food, carrying signals to your phone, whispering in wavelength across space. And at the heart of it all are photons, particles of light, which have no mass, no charge, but infinite reach. A photon born in the core of the sun may take hundreds of thousands of years to escape the dense plasma and reach open space. Once free, it travels to Earth in about 8 minutes, uninterrupted, unbending, unaging. That sunlight on your face, it's ancient. It started its journey long before you woke up, before your house was built, before any word you've spoken today was ever formed. And photons are everywhere. They're emitted when an electron drops to a lower energy level. They move in packets, discrete amounts of energy. The brighter the light, the more photons. The bluer the light, the more energy in each one. Your retina captures these photons. They strike your eye and trigger chemical changes. Those signals become electrical pulses, traveling through your optic nerve to your brain. You don't see light. You feel it. You translate it. You construct an image inside your skull. And so reality becomes experience. Because light obeys rules, but perception interprets them. Now shift your attention again, deeper to the particles beneath particles. Quarks, the smallest known building blocks of matter. They combine in groups of 3 to form protons and neutrons. They come in different types called flavors: up, down, charm, strange, top, and bottom. The proton, for example, is made of 2 up quarks and 1 down quark. Neutrons are 2 downs and 1 up. Their interactions are governed by the strong force and mediated by particles called gluons. Gluons don't just connect quarks, they carry the strong force itself. They're what keep the building blocks of atoms together. And without them, the universe would fall apart. But gluons don't act alone. In fact, inside a proton, the interactions are so intense, it's more accurate to think of it as a churning sea, a turbulent storm of quarks, gluons, and energy. The deeper you go, the less solid matter becomes. You reach a place where mass is just a side effect of energy, where particles flicker in and out of existence, where virtual particles appear for billionths of a second and then vanish again. This is the quantum vacuum, not empty space, but a field of potential, always fluctuating, always active. And from this field perhaps come even stranger forces. Scientists suspect there may be more than just the 4 we know: dark energy, dark matter, unknown dimensions, things we haven't yet touched. Dark matter, for example, makes up most of the universe's mass, and yet we cannot see it, cannot feel it. It does not interact with light. Only gravity gives away its presence. It holds galaxies together. Without it, stars would drift apart. The universe would be thinner, emptier, less stable. But dark matter does not emit, absorb, or reflect light. It is invisible and essential. Then there's dark energy, even stranger, a mysterious pressure that causes the universe to expand faster and faster over time. No one knows what it is, only that it exists, and that it might make up more than 70% of all the energy in the cosmos. The visible universe, the stars, planets, nebulae, galaxies, makes up less than 5% of what's actually there. So most of what exists, we cannot see, cannot touch, can only guess. And yet, here we are, understanding it more with each question we ask, peeling back the layers, mapping the invisible, and listening closely to the whispers of forces we cannot feel directly. Because that's what science does. It builds a picture from shadows. It turns the unseen into understanding, and turns quiet forces into clear truths. Chapter 4. The Blueprint of Life in a Code of 4 Letters. Inside every cell in your body, right now, there's a script. A quiet instruction set written in an alphabet made of chemicals. It tells your body how to grow, how to heal, how to remember, how to breathe. And it all fits into something so small it coils up inside the nucleus of a single cell. That code is called DNA, deoxyribonucleic acid. It's not just a molecule, It's the most elegant storage system ever discovered. And the most amazing thing, it only uses 4 letters, A, T, C, and G, adenine, thymine, cytosine, and guanine. They form base pairs, A with T, C with G. Like magnetic poetry on a double helix, millions, sometimes billions, of these pairs line up in sequences, and each sequence spells out how to build you. Not metaphorically, literally. Your eye color, your blood type, your height, how your liver filters toxins, even your ability to digest certain foods, all encoded, all written in this 4-letter chemical language. A single human cell contains about 2 meters of DNA, coiled so tightly it fits inside something 1,000th the width of a hair. Multiply that by the trillions of cells in your body, and your DNA could stretch to Pluto and back several times. Yet it's not chaotic, it's precisely folded, tagged, packaged, like an infinite library stored in origami. And despite its complexity, it copies itself almost flawlessly. Every time your cells divide, your DNA duplicates, billions of letters get copied, with just a few mistakes per replication. Most are harmless. Some change nothing. A few spark evolution. These tiny changes, called mutations, are how nature experiments, how species adapt, how one generation differs from the last. Mutations are the typos of life. But some typos become poetry. That's how we got feathers, how we got opposable thumbs, how we developed the ability to see color, walk upright, speak, imagine. DNA isn't static. It responds. It activates or silences genes depending on your environment. Stress, food, sleep, trauma, they all influence how your DNA expresses itself. This field is called epigenetics. It studies not what genes you have, but which ones are switched on. 2 people can have nearly identical DNA, but express completely different traits depending on experience. Even identical twins, same genome, can have different fingerprints, different health outcomes, different reactions to life. DNA is the hardware, epigenetics is the software, and your environment is the user. Now zoom in closer, into the DNA itself. It's built on a sugar-phosphate backbone. Each rung in the ladder is a base pair, but inside those rungs, electrons form bonds, hydrogen bonds, fragile yet essential. Even smaller than that, quantum interactions begin to matter. Enzymes that unzip DNA and copy it rely on atomic-level precision. Errors that slip through can lead to cancer, or cure it. All within the chemistry of the cell. And the cell, that tiny chamber where DNA lives, is a bustling city of molecules. Proteins carry cargo, ribosomes build structures, mitochondria generate power, membranes communicate with the outside world. Each cell is alive in the most precise, regulated way imaginable. It listens, it responds, it self-repairs, and every instruction it follows comes from that ancient, coiled script. Your DNA isn't new, it's a remix of your ancestors. You are the latest chapter in a genetic story, billions of years in the making. The same code, ATCG, exists in plants, animals, fungi, bacteria. The structure of DNA is nearly universal. It connects all life. That's how we know evolution is real, because the deeper we look, the more common patterns we find. The same gene that helps a fish grow fins helps you grow fingers. Same code, different context. That code is copied, passed on, and reshuffled through reproduction. Each egg and sperm carries half the instruction manual. When they meet, the code completes. A new book is written, and the first thing that new book does is build a body. From one fertilized cell it becomes 2, then 4, then 16, then a cluster, then tissues, organs, systems, a heartbeat. And all of it, from nothing more than water, nutrients and information, follows the instructions. No designer, no blueprint on a desk, just a molecule that remembers what worked before. DNA isn't conscious, but its history is. It's been tested, shaped, selected, by heat and hunger, by cold and predators, by time itself. And now it resides in you, quietly working, building proteins, replicating cells, passing itself on. But here's where it gets strange. Your cells have the same DNA, yet a brain cell behaves differently from a skin cell. Why? Because of gene expression. Only a fraction of your genes are active in each cell. The rest are silenced, like instruments not playing in the orchestra. And yet they're still there. Every cell in your body contains the entire score. It just chooses which part to play. In that way, your body is a symphony of selective silence, a choir of chemical restraint. Now step back. If DNA is a code, could it be read like software? That's what scientists are doing now, reading genomes, editing them, changing letters. With tools like CRISPR, we can cut and paste genes, turn off diseases, insert new traits. It's precise, powerful, and controversial because the same tool that could cure cancer could also be used to design people, to select height, intelligence, eye color, to erase certain futures and promote others. And so biology meets ethics. The frontier isn't just cellular, it's moral. What should we change? What should we preserve? That's the double helix of the future. Technology and responsibility, twisting together, one base pair at a time. Meanwhile, inside you, nothing has stopped. Right now, your cells are duplicating. Old cells are dying, replaced in quiet waves. Your skin renews every few weeks. Your stomach lining turns over every few days. Some neurons will last a lifetime. Others are refreshed. Your blood regenerates. Your bones remodel themselves. You are not static. You are a process, a flow of matter guided by code, shaped by environment. And when you think, when you imagine, dream, or wonder, your brain is using proteins made from that same genetic instruction. Thoughts are built from chemicals, emotions from ions, memories from molecules, and it all begins with 4 letters. A-T-C-G. A language written without ink. No author. Just billions of years of trial and error. Life doesn't need to know what it's doing, it just needs to do it well enough to survive. And somehow that was enough to produce sight, to produce minds, to produce you, sitting here, breathing, listening. Chapter 5, Consciousness, Thought, and the Illusion of Control. There is a voice in your head. Right now it's reading this to you. Calmly, smoothly, word by word. But, what is that voice? Where does it come from? Who exactly is listening? The mind feels like a single unified thing. A center, a self, a steady awareness, floating in the background of everything. But when we start asking where consciousness lives, science offers no simple answer. The brain, we know, is an organ. It has structure. It has layers, cortex, hippocampus, amygdala. Billions of neurons arranged in patterns, networks, circuits. But those are just parts. None of them alone explain what it feels like to be you. Somehow, within this tangled mass of cells, a sense of awareness emerges. Not just thoughts, not just perception, but the ability to reflect, to observe ourselves observing. This is what philosophers call the hard problem of consciousness. Why should a physical brain give rise to subjective experience? Why does red feel like red? Why does music move us? Why is there anything it is like to be alive? We can trace brain activity. We can monitor what happens when we see, or hear, or speak. But we still don't know why the lights are on, why anything is being experienced at all. Some theories say it's about complexity. But once a system becomes integrated enough with enough internal feedback and structure, consciousness naturally emerges, like heat from friction, or waves from the wind. Others argue it's a fundamental property, that consciousness isn't something brains create, but something they channel, the way a radio tunes into a frequency already present. But whatever the mechanism, your brain does something no machine has yet achieved. It creates a model of reality. It predicts what will happen next, and it includes you inside the model. You don't just experience the world, you experience yourself in the world, from behind your eyes, from within your body. This internal perspective is built from billions of signals, neurons firing in synchrony, chemical exchanges, tiny voltages dancing across synapses, and from that emerges presence, a center, a witness. But here's where it gets more strange. Most of what your brain does happens without you. When you decide to raise your hand, it feels like you made the decision, but experiments show your brain began preparing for that movement, hundreds of milliseconds before you became aware of the choice. In one study, scientists could predict a person's decision before the person consciously knew they'd made it. The brain initiates, then consciousness catches up. So what is free will? Is it an illusion? Are we just narrators, explaining choices we didn't truly make? Some scientists believe the sense of self, the feeling of authorship, is a story the brain tells itself. A compression of all the background processes into one smooth identity. Others argue that even if choices begin unconsciously, conscious thought can still influence outcomes by setting long-term intentions, by overriding habits, by reflecting. In either case, the brain isn't simple. It isn't just one voice. It's a parliament, an ecosystem, multiple systems all working together, and sometimes against each other. You have a conscious mind, but also a subconscious, an emotional brain, a motor brain, a memory system, and they don't always agree. Your conscious mind might say, "I won't eat the cake," but your emotional system, sensing sugar and comfort, begs otherwise. And your body, it responds before thought even arrives. Your heart rate rises, your mouth waters, your hand begins to move. Only afterward does the mind step in and explain it. "I was just hungry. I earned it today. I'll start the diet tomorrow." Rationalization. The mind catching up with the body. And this happens constantly, every day, every moment we act, then explain. We move, then justify. And it all feels seamless. This is the illusion of control. Not total illusion, but partial, because we are not single entities. We are layered. Just like the brain. It evolved in layers, from the reptilian brainstem, which controls breathing, heart rate, basic instincts, to the limbic system, which processes emotion, to the neocortex, the seat of language, logic, and imagination. These layers still exist, they still function, and often, they argue. When you feel conflicted, that's not weakness, that's biology. Different modules offering different plans, different priorities, safety versus risk, comfort versus growth. And somehow, within this swarm of signals, a decision is made, not always the right one, but always a result of negotiation. Now let's talk about thoughts. What is a thought? Not a sentence, not a word, but a firing of neurons in patterns. Each thought is a cascade, a ripple in a network. One part of the brain activates another, which lights up a memory, which stirs an image, which triggers a layel. And then, your language centers kick in. They take the raw experience and turn it into words. That's why we talk to ourselves, to make sense of the storm inside. But language is only one layer. You can feel things you cannot say, know things you cannot explain, solve problems before words arrive. This is intuition. It's not magic. It's experience compressed into signals too fast for conscious unpacking. You know something feels right or wrong, and only later do you find the reasons. This is how pilots, surgeons, chess masters operate, not just with logic, but with trained instinct. The brain learns patterns. Over time it predicts better. It builds shortcuts, and those shortcuts become you, your habits, your style, your voice. Even your sense of self is a pattern, constructed from memory, expectation, sensory input. When those systems break through injury, disease, or trauma, the self can change, dissolve, fragment. People with certain brain injuries forget who they are. Others remember facts, but lose emotion. Some lose the ability to recognize faces, even their own. Others experience split consciousness, as in rare cases of split brain surgery. In those experiments, the two hemispheres of the brain no longer communicate directly. Each side begins to develop its own preferences, its own responses. Two minds in one skull, and the person does not notice. That's how well the illusion works. We feel like one even when we're divided. So what are you? A body? A brain? A pattern in a system? A temporary point of awareness? Science doesn't yet know. But it does know this. Whatever consciousness is, it's delicate, it's rare, and it's temporary. Sleep, for example, silences it. Every night, the light dims, you lose awareness. The world disappears, and yet you do not die. You return. Dreams replace waking thoughts. Time stretches and bends. The rules relax. And then, you wake. Reassembled. Coherent. Back. No other known structure in the universe does this. Planets don't wake. Stars don't reflect. But your brain, it stops and starts again. Which makes it more than just strange. It makes it miraculous. Your brain is only about 3 pounds, mostly water and fat, yet it produces love, memory, language, art, mathematics, dreams, despair, hope. It is not perfect. It forgets. It lies. It repeats mistakes. But it is the most complex known object in the observable universe. 86 billion neurons, each with up to 10,000 connections, trillions of pathways, all firing, all coordinating, to let you sit here now, breathing, thinking, wondering. Consciousness might be temporary. It might be fragile. But in this moment, it is awake. It is present. And it is listening. Chapter 6. The Math Beneath the World. You are surrounded by patterns. You might not see them, but they're there. In the curve of a wave, in the spiral of a galaxy, in the veins of a leaf, even in the timing of your heartbeat. And behind these patterns is something deeper, something quieter, something invisible, yet universal. Mathematics is not just about numbers on a chalkboard. It's the structure beneath reality. It's how the universe behaves, even when no one is watching. Before there was language, before there were names, there was math. Every falling object, every orbiting moon, every echo, every ripple, every ray of light follows mathematical laws. And what's strange is that those laws are not invented. They are discovered. We didn't create them. We revealed them. 2 + 2 = 4, not because we say so, but because that truth exists regardless of language, culture, or species. It would be true here, on Mars, or in a galaxy a billion light years away. So what is math? Is it a tool, a map, or is it the code the universe is written in? Physicists use equations to describe nature, not because equations are poetic, but because they work, because reality obeys them. Take motion. A ball thrown into the air follows a parabolic arc. That curve isn't random. It follows a formula. It obeys acceleration due to gravity, and the initial velocity of the throw. The same formula works for missiles, planets, basketballs, asteroids. It scales across distance and mass, because it's based in structure. Now think about sound. A vibrating string doesn't just make noise, it creates standing waves. Waves with measurable frequency, amplitude, wavelength. Pitch, that's frequency. Volume, that's amplitude. Tone and color, that's waveform complexity. Your ears aren't hearing air, they're hearing math. Vibrations, patterns, transformed into sensation. Light is similar. It travels in waves. The color you see depends on the frequency of that wave. Red is slower. Blue is faster. Ultraviolet is faster still, beyond what your eye can catch. All of it is math. Even color is math. And geometry. It's everywhere. Snowflakes grow in 6-pointed symmetry. Why? Because of the shape of water molecules. Because of the angle of hydrogen bonds. Because of simple math repeating over time. Bees build hexagons, not because they understand geometry, but because hexagons are efficient. They cover space with no gaps. They use the least wax for the most storage. Mathematically optimal. Shells form spirals. Galaxies twist in spirals. Storms swirl in spirals, not random ones, but logarithmic spirals. Spirals where the distance between turns grows consistently. That same spiral appears in sunflowers, in pine cones, in your cochlea, deep inside your ear. It's the same equation, echoed across biology, astronomy, and anatomy. Even chaos is math. The fluttering of leaves, the turbulence in water, the swirl of cream in your coffee. They may seem random, but they're not. They're governed by systems so complex, so sensitive, that tiny differences at the start lead to vastly different outcomes. This is chaos theory. It doesn't mean disorder. It means that under the surface of what looks random, there are rules, equations, just too many variables for the human mind to track. That's where fractals come in. Fractals are shapes that repeat at every scale. Zoom in, and they look the same. Like the edge of a coastline, or the branching of trees, or the capillaries in your lungs. The Mandelbrot set, a famous fractal, is made from a simple formula, but it generates infinite complexity, boundaries that never end, shapes within shapes within shapes. And all of that comes from math. Think now about pi, 3.14, and on it goes. No pattern, no repetition. An infinite, irrational number. And yet, it appears in circles, in waves, in probability, in quantum mechanics. Petro shows up where you least expect it, because the circle is everywhere. Or take the number e, 2.718, and so on. The base of natural logarithms. It governs growth, compounding interest, population change, radioactive decay. It's not just a number, it's a rhythm. Then there's the golden ratio, roughly 1.618. It shows up in art, nature, architecture. It appears in the proportions of the human body, the petals of flowers, even in distant galaxies. Is it coincidence, or is the universe drawn to beauty that fits within math? Now step back further. Physics is built on math. The laws of motion, of thermodynamics, of electromagnetism, all captured in equations. Einstein's famous equation energy equals mass times the speed of light squared isn't just clever, it explains why the sun shines, why stars explode, why atomic bombs work. Because energy and mass are not separate, they are interchangeable, different expressions of the same thing. And quantum mechanics, the study of the very small, is defined by wave functions, probabilities, equations predicting the likelihood of outcomes. Not certainties, just possibilities, shaped by math. This math can be used to describe atoms, electrons, photons, tunneling, entanglement, and yet, no one really knows why the math works so well. Eugene Wigner called it the unreasonable effectiveness of mathematics. He marveled that something created by humans as a mental tool could describe the universe with such accuracy. Some say it means we live in a simulation, that the world is code, that we're in a kind of mathematically structured reality. Others say it's proof that math is more than language, it's the actual operating system of the cosmos. Even biology follows math, the Fibonacci sequence, where each number is the sum of the two before it appears in flowers, shells, fruit, animal horns. Why? Because growth often follows expansion rules, and those rules are mathematical. Heartbeats follow rhythms, brain waves form frequencies, walking is a pendulum, balance is a calculation. Your body isn't just flesh, it's ratios, forces, curves, volumes. It is math in motion. And when it breaks down, we use math to restore it, to model it, to repair it. Medical imaging, built on algorithms, MRIs, CT scans, ultrasounds, they rely on mathematical transformations. Fourier analysis, signal processing, probability distributions. Even vision itself is math. Your retina samples light. Your brain reconstructs an image. It estimates depth, motion, edge, color, like a visual equation solving itself in real time. And sound? Your ears break waves into frequencies. Your brain turns them into meaning. Music is math. Speech is math. Language is patterns of sound over time. Think now of computers. They don't understand words. They understand numbers. Everything you see on a screen, images, text, sound, video, is stored as binary code. Zeros and ones. Math. Even randomness in code isn't truly random. It's generated by algorithms. Pseudo-random, not pure. True randomness is rare, and usually quantum. So the question returns, is the universe fundamentally made of matter or of math? Some physicists suggest that matter is math, that the particle is the formula, that the equation is the thing. If that's true, then you are an equation. A living, moving, self-aware formula, a system of ratios and waves and feedback loops. It's strange, but perhaps not depressing. Because even in numbers, there is elegance, there is harmony, there is infinite possibility. We don't know why math exists, or why it works, only that it does, relentlessly, faithfully, quietly shaping everything. You don't have to see it, you only have to listen to the patterns, to the rhythms, to the equations that breathe behind the world. Chapter 7. The scale of the universe and your place within it. When you look up at the night sky, it's easy to feel small. The stars seem distant, the space between them endless. But what's even more astounding is how much we now understand about that vastness. The universe is not just big, it is bigger than your brain is built to comprehend. And yet, we try. We measure it, map it, model it. all from a small rock, spinning quietly in the darkness. Let's start with distance. The Earth is about 13,000 kilometers wide. That's large, until you compare it to the Sun. The Sun is over 1 million kilometers in diameter. You could fit about 1 million Earths inside it. And yet, the Sun is just an average star, middle of the road, not particularly large, not particularly small. Now consider the distance from Earth to the Moon, about 384,000 kilometers. If Earth were the size of a marble, the Moon would be a small bead, a meter away. The distance to the Sun? 150 million kilometers. That's one astronomical unit, the standard measurement for space inside our solar system. But even that is just local. Light from the Sun takes about 8 minutes to reach us. So when you look at sunlight, you're seeing the past 8 minutes ago. Now travel outward, the outer planets, Jupiter, Saturn, Uranus, Neptune, orbit much farther away. Neptune, the most distant, is about 4.5 billion kilometers from Earth. That's 4.5 hours by light. It's still inside our solar system, and yet already beyond our reach by normal travel. Now past Pluto, and beyond that, the Kuiper Belt, a ring of icy objects circling our system. Then comes the heliopause, the boundary where the solar wind slows and interstellar space begins. The Voyager probes have crossed this threshold. They are now more than 20 billion kilometers from Earth, moving into the darkness with faint signals that still whisper home. But even the entire solar system is just a speck compared to our galaxy. The Milky Way, one galaxy among hundreds of billions, a swirling disk of stars, dust and gas, about 100,000 light-years across. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. So when we say our galaxy is 100,000 light-years wide, we mean it's enormous beyond language. It contains over 100 billion stars, and many of those stars have planets, maybe Earth-like, maybe not. We've only just begun to find them. Our Sun is located in one of the spiral arms, the Orion Arm, roughly midway between the center and the edge. It orbits the galactic core once every 230 million years, a year in galactic terms. Right now, as you listen, our entire solar system is hurtling through space, carried along in this giant whirlpool of gravity and starlight. But the Milky Way itself isn't still. It's moving too, pulled by the gravity of neighboring galaxies. We're on a collision course with the Andromeda Galaxy. In about 4 billion years, the two will merge. Stars are so far apart, they'll mostly pass through each other. Galactic collisions are more like dances than crashes. And beyond that, clusters of galaxies, superclusters, webs of dark matter, holding them in place. The observable universe spans about 93 billion light-years across. And yet, it might be infinite. We can only see what light has had time to reach us. The rest lies beyond our current vision, perhaps forever. This is the scale we live in. A planet orbiting a star, inside a galaxy, drifting through a web of galaxies, in a space that defies the boundaries of thought. Now turn inward. Think about your body. It too exists across scales. Your height is measured in meters, your cells in micrometers, your molecules in nanometers, your atoms in picometers, your quarks in fractions, still unnamed. From the vastness of galaxies to the flicker of particles, you're a midpoint, a bridge between extremes, small compared to the universe, enormous compared to atoms, yet you carry both inside you. You are made of stardust, atoms forged in ancient stars, spread by supernovae, woven into your bones, flowing in your blood. And the scale of time is no less incredible. Your lifetime spans about 80 or 90 years, one orbit of the Earth per year. Each year, a rhythm, birthdays, seasons, history. But the universe has lived through 13.8 billion years. Time enough for stars to be born and die, for galaxies to grow and collide, for life to emerge from molecules. If you compress the entire history of the universe into one calendar year, Earth would form in September, multicellular life in December, humans on December 31st in the last few minutes before midnight. And yet, here we are, looking back, asking questions, building tools that reveal the scale of it all. The telescope lets us see far. The microscope lets us see close. But it's the mind that makes sense of it, that builds models, finds patterns, tells stories. And somehow, our stories match reality. The math works. The predictions come true. We launch probes, and they land. We measure atoms, and they behave. From scale to scale, science connects the dots. It finds unity in diversity. From quark to galaxy, there are laws, structures, constants. Gravity is weaker at small scales. Quantum forces dominate inside atoms. But the rules are still there, adapted to context, rearranged by density, influenced by scale. Even your perception is scale sensitive. You don't notice the Earth spinning, or the molecules vibrating. You live in the middle ground, the human-sized world. But technology lifts that veil. It shows you what your senses can't, and once seen, you cannot unsee it. That's the power of understanding scale. It humbles, it clarifies, it expands the mind. You are not the center, but you are not irrelevant either. You are part of the system, built by it, dependent on it, capable of observing it. You are not just in the universe, you are of the universe. Its matter, its energy, its laws. And when you look up, you are not looking out, you are looking in into a vast reflection of what you already contain. Chapter 8. Evolution, Adaptation, and a Code that Learns. Life didn't begin with complexity, it began with change, with molecules that could copy themselves and then make mistakes. Small errors, tiny shifts, and yet those shifts would change everything. This is evolution, not a theory in the casual sense, but a framework so robust, so predictive, so tested, that it underlies all of modern biology. The core idea is simple. Living things change over time, not randomly, but in response to their environment, their survival, their reproduction. Genes are passed on from one generation to the next. But sometimes genes change. Mutations occur. Most are neutral, some are harmful. But every now and then, a mutation is useful. It gives an advantage, stronger legs, sharper vision, a better immune system, a brain that can plan, and that advantage leads to more offspring, more copies of that gene, more presence in the next generation. Over time, the population shifts, not through planning, but through persistence. This process has no direction, no goal, no final form. It simply favors what works, right now, in this place, under these conditions. It's slow, unpredictable, but relentless. Consider the eye. It didn't appear fully formed. It began with light-sensitive patches on primitive skin. Those cells helped detect shadows. Shadows helped avoid predators, and so, they were useful. Over millions of years, those patches deepened into cups, then closed into chambers. Lenses formed, retinas sharpened. Eventually vision. From jellyfish to eagles, the eye evolved many times. Not once, but over and over. Because the ability to see is useful in almost every niche. That's convergent evolution. Different organisms evolving similar solutions to similar problems. Wings in bats and birds. Fins in sharks and dolphins. Eyes in squids and humans. Different paths. Same outcome. Because physics, chemistry and biology set the rules. Now think about giraffes. Long necks let them reach high leaves. But the length isn't just about height. It's about fighting. Male giraffes swing their necks like clubs in battles for mates. The longer the neck, the more force. And so evolution favored longer and stronger vertebrae. It's not just survival of the fittest. It's reproduction of the most successful. The gene that spreads survives. Even cooperation evolves. In species like wolves, ants, dolphins, working together provides safety, food and success in raising young. Altruism, then, isn't always selfless. It's a strategy. Help the group, and the group helps your genes. But sometimes, evolution takes a stranger path. Creatures develop traits that seem useless, or even harmful, like peacock feathers, bright, heavy, easy to spot. And yet, they signal fitness. I can survive even with this burden. It becomes attractive, and so the feathers persist. This is sexual selection, where traits evolve not for survival, but for desirability. Beauty becomes a survival tool. Now turn inward. Your body is full of evolutionary leftovers. Goosebumps, once used to puff up fur. An appendix once helpful for digesting plants. Wisdom teeth, designed for chewing a tougher diet. All still with you, but not always useful. Even your DNA holds fossils. Pseudogenes, genes that once coded for proteins but now lie dormant. Remnants of ancestors, silenced by time. And yet, life keeps experimenting. Random mutations, sometimes driven by radiation, or error, or chemical stress. Most fail, some succeed, and the process repeats. That's the engine of adaptation. When environments change, drought, cold, predators, species either adapt, move, or die. Darwin's finches, on the Galapagos Islands, had different beaks on different islands. Some were short and strong for cracking seeds, others long and narrow for reaching into flowers. Same ancestor, different pressures, different results. But evolution isn't just slow, it can be fast when the pressure is high. Bacteria evolve resistance to antibiotics in just a few generations. Viruses mutate between hosts. That's how pandemics begin, and how they end. Because adaptation never stops, it doesn't wait, it reacts. And now, we are no longer just products of evolution, we are shaping it. Through medicine, we extend life. Through technology, we alter our biology. We choose mates, not just through instinct, but through apps, ideas, and intention. We modify crops, create synthetic genes, edit embryos. We are rewriting the code. And with that comes responsibility. Because evolution doesn't see the future, it only sees now. But we can imagine what might come. Now think again about DNA. It's not static. It mutates, folds, duplicates. It interacts with proteins, enzymes, and signals. It's regulated by feedback, timing, and chance. And it's influenced by behavior. Stress can change gene expression. So can love. So can fear. This is not just biology. This is learning. Even bacteria can adapt their defenses. The immune system learns. Neural networks grow stronger with repetition. Evolution and learning are cousins. They both work through variation and selection. Try, fail, adjust. Try again. This is the universal algorithm, from proteins folding, to animals migrating, to civilizations advancing. The pattern is the same. And so we see ourselves not as exceptions but as participants. You are not the endpoint of evolution. You are its expression in this moment. A temporary configuration of matter, shaped by time, carrying a legacy. Your eyes evolved to find patterns, your hands to manipulate tools, your brain to model possibility. You are not separate from nature, you are nature in reflective form. You wonder, because wonder had value. Curiosity helped us find food, shelter, fire, and now it helps us explore black holes, design vaccines, and write music. Every thought you have rests on a chain of inheritance that goes back over 4 billion years. And yet, that chain is fragile. Species go extinct, lines end, ideas vanish. So we pass them on, through genes, through stories, through science. This is evolution too, not just of bodies but of knowledge. Memes, ideas that replicate, evolve through culture. Language changes, beliefs mutate, technology adapts. The faster we share, the faster we evolve. Digitally, socially, collectively. You are not alone in this process. You are part of a learning system that stretches across minds, across time. And with each breath you take, you are still evolving. Chapter 9. The chemistry of everything. Everything you see, touch, eat, breathe. It's all made of chemicals. Not just poisons in a bottle, but the very ingredients of reality. Water is a chemical. Air is a mixture of chemicals. Your body is a collection of complex chemical systems, balancing, adjusting, reacting in every moment. And all of chemistry starts with atoms. Atoms are the foundation, not indivisible, as the ancient Greeks once thought, but structured, layered, organized. Each atom has a nucleus, a dense core made of protons and neutrons. Surrounding that nucleus is a cloud of electrons. These electrons don't orbit like planets. They exist in probability zones, regions where they're most likely to be found. The number of protons defines the element. 1 proton, that's hydrogen. 2, helium. 6, carbon. 8, oxygen. And so on, up to over 100 known elements. The periodic table organizes these elements. It's not just a chart, it's a map of behavior. Where an element sits on that table tells you how it reacts, how it bonds, what it tends to form. Some elements are noble like neon and helium. They don't easily form compounds, others are highly reactive like fluorine, sodium or chlorine. And chemistry begins when atoms bond. A chemical bond is a connection between atoms. It happens when electrons are shared or transferred. Covalent bonds share electrons, like a handshake. Ionic bonds transfer electrons like a gift. Water is a simple molecule, 2 hydrogen atoms bonded to 1 oxygen. But its behavior is not simple, it's polar. One side is slightly negative, the other slightly positive. This polarity lets water stick to itself. That's why it forms droplets. It's why insects can walk on it. It's why it climbs up trees, against gravity, carrying nutrients from root to leaf. Water also dissolves many substances. It's called the universal solvent. It pulls apart ions, wraps them in a shell of polarity, and carries them away. That's why blood, made mostly of water, can transport salts, sugars, oxygen, hormones, all dissolved, all in motion. Now consider carbon. Carbon is the backbone of life. It has 4 bonding sites, which means it can form chains, rings, branches, simple or complex, rigid or flexible. Carbon can link with hydrogen, nitrogen, oxygen, sulfur, phosphorus. It can form millions of different compounds, proteins, fats, sugars, DNA, all based on carbon. Organic chemistry is the study of carbon compounds. It's where biology and chemistry overlap, where molecules take on function, where information hides in shape. A small change in a molecule, just 1 atom swapped, or a twist in the structure, can change a medicine into a poison, or a hormone into a signal, or a sugar into a toxin. That's how precise chemistry is. Not just what elements are present, but how they're arranged. The geometry matters, the orientation, the 3D shape. Your body reads these shapes. A protein must fold just right to do its job. An enzyme must fit its target, like a key fits a lock. A receptor on a cell waits for a specific chemical messenger. That's biochemistry, where molecules carry meaning, where chemistry becomes behavior. Let's talk about reactions. A chemical reaction is when bonds are broken and formed. Reactants go in, products come out, heat might be released. An exothermic reaction, or absorbed, an endothermic one. Some reactions are fast, like explosions. Some are slow, like rust. Some require energy to start, others happen spontaneously. In your body, reactions happen all the time. Digesting food, contracting muscles, thinking thoughts, all made of molecules reacting. And all controlled by enzymes. Enzymes are biological catalysts. They speed up reactions without being consumed. They lower the activation energy, the barrier that must be crossed. Without enzymes, life would crawl. With them, it hums. Fast, efficient, precise. Each enzyme is specific. 1 enzyme for 1 reaction. It binds to its target called a substrate, does its work, and moves on. Temperature affects enzymes, so does pH. Too hot, too acidic, and they denature, lose their shape, lose their function. That's why your body maintains homeostasis, a stable internal environment. Chemical balance is delicate. Life depends on it. Now consider acids and bases. An acid donates hydrogen ions, a base accepts them. The pH scale measures this. From 0 to 14, 7 is neutral, lower numbers are acidic, higher numbers are basic. Your blood stays around 7.4, your stomach acid around 1 or 2. Different zones, different chemistry. Buffers help keep pH stable. They absorb excess hydrogen or hydroxide ions. They resist change. That's their job. Stability and motion. Now step into your cells. They are chemical factories, powered by mitochondria, which convert glucose into energy. That energy is stored in a molecule called ATP, adenosine triphosphate. 3 phosphates, held by high-energy bonds. Break one off, and energy is released. Your muscles use ATP. So does your brain. Every heartbeat, every breath, powered by a stream of chemical conversions. And when cells need to send messages, they release neurotransmitters, tiny chemical couriers, dopamine, serotonin, acetylcholine. Each one binds to a receptor and changes the state of the cell. Your mood, your memory, your attention, all influenced by chemistry. Hormones do similar work, but at a distance. Released into the bloodstream, they travel far, telling tissues to grow, or to slow down, or to prepare for stress. Adrenaline spikes your heart rate, insulin helps absorb sugar, melatonin tells your body it's time to sleep, all through chemistry. Even emotion is chemical. Love involves oxytocin, fear triggers cortisol, happiness releases endorphins, sadness lowers serotonin. And yet, these chemicals don't control you. They influence you. They are part of the system, not the whole story. Your thoughts can change your chemistry, and your chemistry can change your thoughts. This two-way street between mind and molecule is still being explored, still being mapped. And at every step, chemistry connects it all. The food you eat becomes fuel. The oxygen you inhale fuels combustion. The carbon you exhale once lived in plants. And before that, in the atmosphere. And before that, inside the earth. The atoms in your body are not new. They are ancient. They have been part of stars, volcanoes, oceans, dinosaurs. You are made of chemicals that have been many things. Stone, flame, cloud, bone, now arranged as you. And someday, those atoms will be rearranged again into something new, someone else, another form. Because chemistry doesn't stop, it only transforms. Chapter 10. Electricity, magnetism, and the invisible threads of reality. You don't see it, you don't touch it, but it's there, surrounding you, moving through you, powering everything you do. Electricity. It isn't just wires and light bulbs, it isn't just the buzz of machines. Electricity is one of the fundamental ways the universe expresses energy. And it's happening right now, in your nerves, in your brain, in the air. Electricity begins with charge. There are two kinds, positive and negative. Opposites attract. Likes repel. That simple rule, so basic, builds the foundation of electromagnetism. Electrons carry negative charge, protons carry positive. Neutrons have none, and when electrons move, they create current. Single electron is unimaginably small, yet together, in numbers beyond counting, they form lightning, circuits, electric fields. They power cities. They fire signals across your mind. Inside your body, electricity is life. Nerve impulses are electric events. Your heartbeat is triggered by an electrical signal from the sinoatrial node. Muscles contract because of ion exchange. Thoughts move through networks of neurons on currents, so faint they can be measured and mapped. Now, imagine a wire, electrons drifting through it, pushed by voltage. This drift, slow, steady, creates energy that flows fast. The signal moves quickly, even though the particles move slowly. Voltage is the potential difference, like water pressure. Current is the flow, like the stream of water. Resistance slows it down, like a narrow pipe. Ohm's law connects these ideas. Voltage equals current times resistance. It's not magic, it's math. And it governs how every device around you works. Your phone, your lamp, the circuits in your watch, the neurons in your brain, all obey this simple relationship. And then there's magnetism, the quiet sibling of electricity. It shows up when charges move. It surrounds wires with invisible lines. It bends light. It guides compasses. Magnetism and electricity are not separate forces. They are two sides of the same coin. Electromagnetism. Move a wire through a magnetic field, and electricity is induced. Run electricity through a coil, and you get a magnetic field. This is how generators work. Turbines spin, wires move through magnets, and energy is created. It powers cities. It lights homes. It charges lives. It also explains how motors run. Electricity produces a magnetic field, which spins a rotor, which moves a machine. Everything from wind turbines to electric toothbrushes to satellites all harness this unity of force. The connection between electricity and magnetism was discovered through centuries of observation, but it was James Clerk Maxwell who revealed its beauty. He wrote 4 equations, the Maxwell equations that describe the entire behavior of electric and magnetic fields, 4 elegant truths that explain everything from light waves to radio signals. Those equations showed something stunning, that light itself is an electromagnetic wave, a pulse of electric and magnetic energy, self-sustaining, traveling through space at the speed of light. So when you turn on a flashlight, you are releasing electromagnetic waves. When you speak into a phone, those waves carry your voice. They move through air, through walls, through vacuum. And they do it invisibly. The spectrum of electromagnetic waves is vast and varied. From the longest radio waves to the shortest gamma rays, visible light is just a sliver, red at the low end, violet at the high end. Everything beyond that remains unseen by the naked eye. But technology makes them visible. Microwaves cook your food, infrared reveals heat, ultraviolet sterilizes, X-rays look inside the body, gamma rays show us cosmic events. All the same force, just at different frequencies, different energies. This is how we see the universe, not just through light, but through all the ways electromagnetic energy interacts with matter. And what is matter, if not particles wrapped in charge? Every atom has electrons. They repel or attract other electrons. They create electric fields, even when standing still. When they move, they create magnetic fields. When they accelerate, they radiate energy. This is how antennas work. Vibrating electrons create waves which ripple through space, picked up by receivers tuned to the same frequency. And resonance. Resonance is when things vibrate together. A tuning fork, a glass shattering under sound, an antenna receiving just the right signal. Even atoms resonate. They absorb and release energy at specific frequencies. These are called spectral lines, unique to each element. By studying those lines, we learn what stars are made of, what planets are breathing, what galaxies are forming. All by reading light, all by watching electrons jump. In the center of this science is the photon, the quantum of light. A massless, chargeless particle, carrying energy, moving always at the same speed. Photons don't age. They experience no time. They leave a star, cross the void, and arrive in your eye, unchanged. This is the strange edge between physics and perception. Electricity powers your neurons. Light delivers the world to your retina. Magnetism guides birds across oceans, and aligns iron in rocks to record Earth's history. Even animals use it. Sharks detect electric fields in water. Birds sense magnetic fields during migration. Eels generate electric shocks. Life is not separate from physics. It uses physics. It's built from it. And every living moment is charged with energy. Now think about your thoughts. They are patterns of electric activity, measurable, trackable. Electroencephalograms, EEGs, record these brain waves, delta waves during sleep, beta waves during focus, alpha waves during calm. These rhythms shape mood, state, awareness. And though electricity flows inside you, you never feel it. Not directly. Only its consequences: movement, memory, sensation. And in that way, you are an electrical being. Flesh and salt, yes, but also spark and signal. Your body is a circuit. Your heart is a pulse generator. Your mind is a mesh of loops and feedback. And all of it is powered by moving charge. This is why defibrillators can restart a heart. Why a sudden shock can end a life. Why electric fields can guide growth, heal wounds, and synchronize cells. It's why deep brain stimulation can ease tremors. Why electrical implants can restore hearing. Why nerve signals can be mimicked, amplified, or rewrote. We are learning not just to understand electricity, but to communicate with it. And in doing so, we step closer to the fabric of the world, to the invisible threads that bind motion to meaning. Because electricity is not just a force, it's a language, the original language, spoken by atoms, written in sparks. Chapter 11. Sound, Vibration, and the Physics of Hearing. Close your eyes and listen. The world isn't silent, it moves. And wherever there's motion, there's vibration. Wherever there's vibration, there's sound. Sound is not a thing, it's a movement, a ripple through matter. Air, water, steel, they all carry sound. but only if something first moves. A sound begins when something vibrates. A guitar string, a vocal cord, a falling tree. It pushes on nearby air molecules, which push on others, and others still. That push travels outward. A pressure wave, a momentary compression of air, followed by a release, a wave of energy, but not of matter. The air doesn't travel to your ear, it just passes energy along. Each molecule moves slightly, then returns to place, but the wave continues. This is called a longitudinal wave, the kind of wave where the motion of particles is in the same direction as the wave travels. It's different from light, which moves as a transverse wave. The speed of sound depends on the medium. In dry air at room temperature, sound travels at about 340 meters per second. Faster in water, much faster in steel, because denser materials pass vibrations more efficiently. But no medium, no sound. In the vacuum of space there is no air to push, no molecules to carry the wave. So space is silent. Utterly. Now think of your ear, a biological marvel designed to translate vibration into thought. Sound waves enter the ear canal and strike the eardrum, a thin membrane that vibrates in sync. Those vibrations move three tiny bones, the hammer, anvil, and stirrup, amplifying the sound and sending it to the cochlea, a spiral-shaped chamber filled with fluid. Inside the cochlea are tiny hair cells, not like the hair on your head, but sensory receptors that respond to specific frequencies. Each hair cell is tuned to a certain pitch. When it's triggered, it sends a signal to the brain. The brain maps these signals and builds the sensation of sound. Pitch is determined by frequency. The faster the wave, the higher the pitch. Low notes are slow, high notes are fast. Volume is determined by amplitude, how much energy the wave carries. Whispers are small waves. Thunder is large. The human ear can hear frequencies from about 20 Hz to 20,000 Hz. Below that, called infrasound, is used by elephants, whales, volcanoes. Above that, ultrasound is used by bats, dolphins, and medical imaging. Some animals hear better than we do. Dogs hear higher frequencies. Owls hear directionally, using asymmetrical ears to locate prey with terrifying accuracy. And yet, our hearing is sensitive, delicate, capable of detecting a pin drop or the subtle titterus between musical notes. Music itself is just organized sound, waves in harmony, patterns in frequency, rhythm and tone. A melody is a sequence of pitches. A chord is multiple waves layered together. A beat is rhythmic energy, repeating in time. Music moves us, not just emotionally, but physically. Our bodies synchronize to rhythm. Our brain releases dopamine in response to harmony. Memory, motion, feeling, all tied to sound. Why does a minor chord sound sad? Why does a dissonant interval feel tense? Why do certain rhythms make us move? These are questions still being studied. Some believe it's cultural, others think it's neurological. Maybe both. Maybe music is part of our design. A shared language of vibration. Now think about echo. An echo is a sound wave bouncing back. It reflects off surfaces, walls, cliffs, canyons, and returns with delay. If the surface is far enough away, you hear it as a separate sound. Echoes help us map the world. They're used in sonar, in echolocation, in medical scans. Sound bounces differently depending on the surface. Soft absorbs, hard reflects. That's why an empty room echoes, and a carpeted one does not. Reverberation is similar, but with many reflections, close together. The sound lingers, smears over time, filling the space with richness. Acoustics is the science of how sound behaves in space. Concert halls are designed with this in mind. So are recording studios, cathedrals, even classrooms. Sound can cancel itself out. This is destructive interference. When two waves of opposite phase meet, they subtract from each other. This is how noise-cancelling headphones work. They produce a wave that's the mirror image of incoming noise. The result, silence. Sound can also amplify itself. Constructive interference. Waves aligned. More volume, more impact. And sound carries power. In some cases, dangerous power. Infrasound can shake buildings. Resonant frequencies can break glass. Explosions can damage organs. Sound can be used as a weapon or a tool. Now consider speech, a miracle of biology and sound. The brain commands muscles in the chest, throat, tongue, lips. Air is pushed through the vocal cords. They vibrate. The shape of the mouth changes, and words emerge. Speech is layers of sound, pitch, rhythm, emphasis. Tone carries emotion, inflection carries intent. We don't just hear words, we hear feelings. Language is vibration wrapped in meaning. Different languages use different sounds, different rhythms, even different pitches. Some are tonal, like Mandarin, where pitch changes the word itself. Others are stress-based, where emphasis shifts meaning. All are rooted in the same thing: air, shaped by anatomy, pushed into vibration. Even silence can carry weight. A pause in speech, a breath before a note. The absence of sound can be just as meaningful. Now think again about vibration. Everything vibrates to some degree. Atoms are never still. Thermal energy is vibration. Sound is just the vibration we can hear. And every object has a natural frequency, its resonant frequency. Tap a glass and it rings. Strike a bell and it sings. Each shape, each material, has its own voice. Musical instruments are built on this. Strings, wood, air columns, designed to vibrate, to amplify, to resonate. Even the earth vibrates. Seismic waves ripple after quakes, the planet rings, ever so faintly, and we record it to learn what lies beneath. Your own body has resonance. Your chest, your vocal cords, your skull. Your voice is the sound of your structure, and your heartbeat? It produces waves, low-frequency pulses. Your lungs, too, your footsteps, your whisper, all part of a world in motion. The science of sound extends into medicine, architecture, warfare, art. It touches every discipline. It is everywhere. Yet sound fades, it needs a medium. It travels fast, but not forever. It disperses, it loses energy, and then it's gone. But while it lasts, it carries stories, emotion, memory, structure. You are built to sense it, to respond, to speak, to sing. And in every sound you hear there's physics, there's biology, there's vibration, and sometimes there's something more. Chapter 12. Sleep, Dreams, and the Science of Letting Go. Every day ends the same way. Your eyes grow heavy, your thoughts slow down, and eventually you let go. Sleep is not shutting down, it's not turning off. It's a complex, active process, a cycle of transformation that restores, regulates, and rewires. You spend about a third of your life asleep. That means if you live to 90, you'll sleep for 30 years. And yet, for centuries, no one truly understood why. Why do we sleep? Why do our bodies insist on this fragile, vulnerable state, where awareness fades, control is surrendered, and reality bends? Only in recent decades have scientists begun to answer, and what they've found is astonishing. Sleep is not one thing. It's made of stages. Each night you cycle through these stages again and again, about 4 to 6 full cycles in total. The first stage is light sleep. Your brain begins to slow, muscle tone decreases, you drift. The second stage deepens the disconnect. Body temperature drops, heart rate slows, brain waves shift into what are called sleep spindles. Brief bursts of activity that may help consolidate memory. Then comes deep sleep, also called slow wave sleep. Delta waves dominate. Large, slow electrical rhythms pulse through the brain. This is where the body heals, tissue repair, immune strengthening, growth hormone release. Waking from deep sleep is difficult. You may feel groggy, disoriented, because the brain is far from wakefulness. And yet, this stage is essential. Without it, you feel physically drained. But the most mysterious stage is REM, rapid eye movement sleep. This is where dreams bloom. Your brain becomes highly active almost as much as when awake. Eyes flicker beneath closed lids. Breathing becomes irregular. Heart rate rises. And yet, your body is paralyzed. Your muscles are switched off. This keeps you from acting out dreams and protects you from harm. In REM sleep, you dream vividly. Emotions are strong. Logic fades. Time stretches. And dreams are their own world. No one fully knows why we dream. Some theories say it's mental housekeeping. the brain sifting through memories, pruning, sorting, linking. Others say it's emotional processing, a theater for feelings we couldn't face during the day. Some even suggest dreams help with problem solving, testing scenarios, exploring patterns, running quiet simulations. Whatever their purpose, dreams feel real. The mind accepts them. The impossible becomes normal. You fly, you fall, you speak to people long gone, and then you wake. The dream collapses, details vanish, and you return to the world with only fragments. REM sleep becomes longer in the second half of the night, so your most complex dreams usually happen in the early morning hours. Sleep cycles shift with age. Newborns spend half their sleep in REM. Adults, less so. Elderly people often experience lighter sleep, with fewer deep waves. And sleep needs vary. The average adult needs 7 to 9 hours, less than 6 impairs memory, reaction time, and even immune function. Sleep deprivation builds up a sleep debt. It accumulates, and though you can repay some of it, chronic loss takes a toll. Cognitive fog, irritability, weakened focus, reduced empathy. The brain needs rest to work. Sleep also plays a role in memory. During sleep, the hippocampus replays events from the day. This reactivation helps store long-term memories in the cortex. Sleep doesn't just protect what you learned, it organizes it, strengthens it, even enhances creative connections. Have you ever gone to bed with a problem and woken up with clarity? That's the brain, working while you rest. Another key process happens during sleep, glymphatic clearance. It's like a rinse cycle for your brain. Cerebrospinal fluid washes through neural tissue, clearing out metabolic waste and proteins linked to diseases like Alzheimer's. This cleaning system is 10 times more active during sleep. You're not just resting, you're repairing. And yet, we resist sleep. Modern life pushes against it. Blue light from screens delays melatonin release. Stress activates cortisol. Irregular schedules confuse the circadian rhythm. But the body remembers, it keeps time. Your internal clock. The circadian rhythm follows roughly a 24-hour cycle, synchronized by light. Morning light resets the rhythm. Signals travel from the eyes to the suprachiasmatic nucleus, a tiny region in the hypothalamus that coordinates sleep hormone release, temperature, alertness. Melatonin, the sleep hormone, rises in darkness. It makes you drowsy, signals your body to prepare. And yet, you're not a machine. You're flexible. The rhythm can shift, with travel, with age, with habit. Some people are night owls, others are early birds. These tendencies are partially genetic, but they can be trained. Sleep hygiene, the science of good sleep, encourages consistent timing, limited light at night, and calming routines. Even temperature matters. The body prefers to sleep cooler. A drop in core temperature signals it's time to rest. So baths, dim lights, soft sounds, they're not just comforting, they're cues, biological invitations to step into the cycle. And what about sleep disorders? Insomnia, sleep apnea, narcolepsy, parasomnias, they disrupt the rhythm. Insomnia can be stress-driven. A racing mind, a restless body. Sleep apnea interrupts breathing, causing repeated micro-awakenings, often undetected, but exhausting. Narcolepsy is a disorder of sleep regulation, causing sudden sleep episodes, sometimes with cataplexy, muscle weakness triggered by emotion. Parasomnias include sleepwalking, night terrors, and REM behavior disorder, where muscle paralysis fails, and dreams spill into movement. Sleep is fragile, but it's also resilient. The brain seeks it, protects it. Even when deprived, the body prioritizes deep and REM sleep in recovery. Sleep is universal. Every mammal needs it. Birds sleep with half their brain awake. Dolphins too. Some insects sleep. Even plants follow circadian rhythms. Sleep may be the oldest ritual on Earth, older than language, older than tools, a biological reset. And dreams? They cross species too. Rats dream of mazes. Birds replay songs. Dogs twitch in REM, chasing something only they can see. You're part of that same legacy. Every night, you slip into a world you did not design, but always return to. To do. not command sleep. You allow it. You surrender. You let go. And in that letting go, the body heals. The mind clears. The world softens. Sleep is not escape. It's restoration, not absence, but transformation. And in a few minutes, you'll begin that cycle again. A quiet passage into the most essential science of all. Chapter 13. Time, clocks, and the precision of the universe. Time feels constant. It flows. You wake, you work, you rest. But underneath that flow is something far more precise. A universe that keeps time with an accuracy you rarely notice. From the rotation of planets to the ticking of atomic clocks, time is measured everywhere. And the ways we measure it shape our understanding of reality itself. Long before watches or calendars, people looked to the sky, the rising sun, the waxing moon, the changing stars. Time was written in light and shadow. The day, based on Earth's rotation, the year, based on Earth's orbit around the sun, the month, once tied to the phases of the moon, even the week, 7 days, likely rooted in ancient astronomy. But those are approximation, natural rhythms. Yes, but not precise. Not enough for science. Not enough for satellites, GPS, or measuring particle decay. So humans invented clocks, first with water, then sand, then gears, pendulums, quartz, and now, an atomic clock is the most accurate timekeeping device ever built. It doesn't rely on gravity or motion. It uses the vibration of atoms, usually cesium or rubidium, as a metronome. These atoms absorb and emit energy at exact frequencies, billions of cycles per second, so consistent, so stable, they can define a second. In fact, that's how we define it today. 1 second equals exactly 9,192,631,770 oscillations of a cesium atom's radiation. It's not based on Earth anymore. It's based on physics, on the unchanging rhythm of matter itself. And that matters, because time is not universal, it bends. Einstein showed us that time slows down with speed, and it slows down in stronger gravity. Speed. This is not theory anymore. It's measurable. Atomic clocks flown on planes tick slower, clocks on satellites tick faster than those on Earth. Both require corrections. That's how GPS works. It uses multiple satellites to triangulate your location. Each satellite carries its own atomic clock. If even one was off by a fraction of a second, your location would drift by kilometers. So relativity is part of daily life now. Every time you check your map, you're relying on Einstein. But clocks don't just measure, they synchronize. Networks, computers, financial systems all depend on shared time. Stock markets time trades to microseconds. Data centers require exact sequencing. Air traffic, power grids, communication systems. They all trust the clock. And our brains, in their own way, keep time too. You have internal timers, circadian rhythms, ultradian rhythms, biological pulses. The suprachiasmatic nucleus in the hypothalamus acts as your master clock. It coordinates sleep, hormone cycles, body temperature. It syncs with daylight through signals from your eyes. But there are local clocks too, in your liver, your skin, even your immune cells. Tiny molecular loops that oscillate, tick by tick. This internal timekeeping affects how medicines work. When you heal best, when you learn most easily, your body is not timeless. It runs on schedule. Even memories are time-stamped. Your brain tags events with rough temporal information. What happened first? What came later? And perception of time can stretch or compress. In fear, moments feel long. In boredom, minutes crawl. In joy, hours vanish. Time is not just external, it's emotional. Now, think smaller. At the quantum scale, time behaves differently. Some equations in physics don't even include time. They are timeless, static. So where does time come from? One idea. Entropy. As disorder increases, we perceive time passing, from order to chaos, from possibility to history. This is the arrow of time, defined not by the ticking of a clock, but by the direction of change. If you watched a glass shatter, you'd know which way time moved. But if you watched atoms vibrating, you couldn't tell. Time, at its core, may not flow. It may be a feature of how we observe. The block universe theory suggests that past, present, and future all exists simultaneously. We just move through it, slice by slice. If true, then your entire life is already there, beginning to end. You just experience it sequentially. That's not how it feels. We feel the pull of the future, the weight of the past, the uncertainty of now. But that feeling might be the mind's translation of a deeper geometry. In deep space, astronomers use time to look backward. Because light travels at a finite speed, the farther we look, the older the light. Galaxies millions of light years away show us what they looked like millions of years ago. The cosmic microwave background is light from nearly 14 billion years ago, a whisper from the beginning. So telescopes are time machines, not because they manipulate time, but because they receive it. And we too are made of time, not just particles, but the intervals between them, the rhythms of interaction, the pulse of physics. Your heart beats, not randomly, but in waves. Your breath cycles, not as a choice, but as a tempo. Your thoughts form in pulses of electrical activity, oscillations, frequencies, alpha, beta, delta, brainwaves, with measurable time signatures. Even silence has a timing. Time is the space between events. It is the measure of change. Without it, motion cannot exist. Cause cannot lead to effect. And yet, if time can slow, can bend, can differ from one observer to another, what is it really? Is it a dimension? An illusion? A byproduct of entropy? Physics still doesn't agree. Some theories unify time and space. Others question whether time is real at all. But clocks keep ticking. Atoms keep vibrating. We measure, we compare, and we build a world on top of rhythm, time zones, calendars, seasons, appointments, reminders, all of them, artificial divisions on something we still don't fully understand. And yet we trust time. We live by it. Mark birthdays, set alarms, celebrate anniversaries, because even if it bends, even if it's not absolute, it connects us. We live in the same hour, the same minute, the same now. Chapter 14, Thermodynamics and the Laws that Govern Energy. At the foundation of physical science lies one of the most essential frameworks ever discovered, thermodynamics. It is not merely a study of heat, it is a precise science of energy, its movement, its transformation, its limits. All matter contains energy, and that energy is always governed by specific rules. These rules are universal, whether you are observing a star, a steam engine, a melting ice cube, or a neuron firing, thermodynamics is at work. There are 4 formal laws of thermodynamics. They are often numbered 0 through 3. Each law builds on the previous one. Each is derived from observation, not theoretical assumption. The 0th law is about thermal equilibrium. It states, if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is also in thermal equilibrium with object C. This is transitivity applied to temperature. It allows us to use thermometers. It forms the basis for comparing temperatures in the first place. The first law is about energy conservation. It states that energy cannot be created or destroyed, only transferred or transferred. This is a general form of the law of conservation of energy. It applies to closed systems, systems where no matter enters or exits. When a system gains heat, that energy must either increase internal energy or do work on the surroundings. Mathematically, this is written as change in internal energy equals heat added minus work done by the system. It applies to engines, to cells, to stars. Energy always has a destination. It cannot vanish. The second law introduces the concept of entropy. Entropy is a measure of disorder, technically the number of microscopic configurations that correspond to a system's macroscopic state. This law states, in an isolated system, entropy always increases, not sometimes, always. This is the arrow of time. It gives time its direction. You can mix cream into coffee, but you cannot unmix it. You can let heat flow from a hot object to a cold one, but not the reverse without adding energy. Entropy tends to increase. This is why perpetual motion machines are impossible. You cannot get more energy out than what you put in, and some of that energy will always be lost as heat. The third law states, as the temperature of a system approaches absolute zero, the entropy of a perfect crystal approaches zero. Absolute zero is 0 Kelvin theoretically. It is the point at which all molecular motion stops. However, reaching absolute zero is impossible. Even with advanced cooling techniques, like laser cooling and adiabatic demagnetization, You can only approach it, never attain it. This sets a fundamental limit. There is a minimum temperature, a minimum entropy, a boundary you cannot cross. These four laws form the bedrock of physical chemistry, engineering, astrophysics, and biology. They are not suggestions. They are principles derived from consistent measurement. Let's examine heat engines, devices that convert thermal energy into mechanical work. A steam engine is a classic example. It uses heat to boil water, generating steam. The expanding steam moves pistons, which turn wheels. But no engine is 100% efficient. According to the second law, some energy is always lost, as waste heat. The maximum efficiency of a heat engine depends on the temperatures of the hot and cold reservoirs. This is known as the Carnot efficiency. It is expressed by the equation 1 minus the temperature of the cold reservoir, divided by the temperature of the hot reservoir. Both temperatures must be in Kelvin. This is the upper limit. Real engines perform below it. In biology, thermodynamics governs metabolism. Cells convert chemical energy into work. Adenosine triphosphate, ATP, is the primary energy currency. Its breakdown releases energy to drive cellular functions. But even cells lose energy. They radiate heat. They follow the same rules. The second law applies everywhere. In cosmology, entropy explains the fate of the universe. As stars burn, as systems decay, the total entropy increases. Eventually, energy becomes evenly distributed. This is the heat death, the state of maximum entropy, minimum usable energy. Even black holes obey thermodynamic laws. They have temperature. They emit radiation predicted by Stephen Hawking. And they have entropy, proportional to the surface area of their event horizons. This leads to the holographic principle, a theory suggesting that all the information in a volume of space can be described by data encoded on its boundary, a thermodynamic insight that reshaped modern physics. In the lab, thermodynamics explains refrigeration. Cooling is not the absence of heat, but the removal of it. Refrigerators do work to pump heat out of a closed space, moving it into the surroundings. The same principle powers air conditioners and heat pumps. They move thermal energy, not just generate it. Efficiency is measured in terms of energy used versus heat moved. Even weather patterns are thermodynamic systems. Warm air rises, cool air sinks. Pressure differences drive wind. Humidity affects latent heat. Storms, hurricanes, climate, all are shaped by energy gradients. Thermodynamics dictates how energy distributes in the atmosphere. In chemistry, thermodynamics predicts whether reactions are spontaneous. This depends on Gibbs free energy, a value that combines enthalpy and entropy. If the change in Gibbs free energy is negative, the reaction is spontaneous. If positive, it is not. This governs everything from combustion to protein folding. Statistical mechanics connects thermodynamics with particle behavior. It treats entropy as the number of microstates, the different ways particles can be arranged. It explains why gases expand, why heat flows, why systems tend toward equilibrium. It adds clarity to the macroscopic laws. Thermodynamics is not only theoretical, it has practical implications from engines to energy policy, from planetary science to nanotechnology. It tells us what is possible, what is probable, and what is forbidden. The laws are never broken. They are the constraints of the universe. Every breath you take, every calorie you burn, every star you observe, all of it dances to the rhythm of thermodynamics. Chapter 15. Quantum Tunneling and the Science of the Impossible. Imagine a wall, a solid barrier. In the classical world you either climb over it or bounce off it. But in the quantum world, particles sometimes go through it. This is not a metaphor, this is quantum tunneling, a real, observable phenomenon, where particles bypass energy barriers. They seemingly don't have enough energy to cross. It defies classical logic. It obeys quantum probability. To understand tunneling, we first must understand the nature of particles at the quantum scale. A particle is not a tiny solid ball. It is a quantum object, described by a wave function. The wave function is a mathematical expression that encodes all the possible positions and energies of a particle. It does not tell you exactly where the particle is. Instead, it gives you a probability distribution, where the particle might be. Where the wave function has high amplitude, there's a higher chance of finding the particle. Where it's low, the chance is smaller, but never exactly zero, unless the wave function itself is zero. Now imagine a particle approaching a barrier. Classically, if its energy is less than the barrier height, it should bounce back. But quantum mechanically, the particle's wave function does not simply end at the wall. It decays into the barrier, losing amplitude exponentially, and if the barrier is thin enough, the wave function doesn't vanish entirely. It reappears on the other side. This means there is a non-zero probability that the particle appears beyond the barrier, despite never having the classical energy to pass through it. That is tunneling. No digging, no breaking, just quantum probability and the weirdness of wave functions. This effect is not just theoretical, it has been experimentally verified countless times, and it plays a fundamental role in the functioning of the universe. One real-world example: alpha decay in radioactive atoms. In certain unstable nuclei, an alpha particle, 2 protons and 2 neutrons, wants to escape, but it is trapped in a potential well created by the strong nuclear force. Classically, it doesn't have the energy to climb out, but the quantum wave function of the particle extends beyond the barrier, and so occasionally it tunnels through. The atom decays. The rate of decay can be predicted using tunneling equations. It matches observation with extraordinary precision. Another everyday technology using tunneling diodes and scanning tunneling microscopes. A tunneling diode exploits the quantum effect to produce ultra-fast switching, used in high-frequency electronics. The scanning tunneling microscope, or STM, uses a sharp metallic tip brought extremely close to a conductive surface. Electrons tunnel across the tiny gap, producing a measurable current. By scanning the tip across the surface, the STM builds an image of the atomic landscape down to individual atoms. We can see the topology of matter thanks to tunneling. But tunneling goes deeper. It plays a role in nuclear fusion, the process that powers the sun. In the sun's core, temperatures reach millions of Kelvin. Still, the kinetic energy of the protons there is not classically sufficient to overcome their mutual electrostatic repulsion. Protons are both positively charged. They repel strongly. But quantum mechanics offers a loophole. Because their wave functions overlap, there is a finite probability that 2 protons tunnel through the repulsive barrier and undergo fusion. Without tunneling, nuclear fusion in stars would require much higher temperatures than we observe. Tunneling is the quiet enabler of the universe's energy source. Now think about quantum computing. Quantum bits, or qubits, use quantum superposition and entanglement to represent multiple states at once. But quantum tunneling is a challenge here. Uncontrolled tunneling can cause quantum decoherence, where qubit states are lost to the environment. But paradoxically, tunneling is also used to create quantum logic gates, where qubits interact based on quantum probability. Designing stable systems means balancing isolation and connectivity, often involving tunneling barriers engineered at the nanoscale. We're building machines that use and protect tunneling simultaneously. In chemistry, tunneling explains reaction rates in certain cold or quantum-sensitive environments. For example, in enzyme reactions, protons or even heavier particles can tunnel through energy barriers, affecting how fast reactions proceed. This kind of tunneling becomes dominant at low temperatures, where thermal energy is insufficient to drive classical transitions, and there's even speculation that quantum tunneling could affect processes in the human brain. While no definitive quantum brain model exists, some researchers propose that electron tunneling within neural proteins could play a role in consciousness or perception. It remains a hypothesis, not a proven model, but it shows how deeply tunneling could reach. Tunneling is also involved in quantum annealing, a method used to solve optimization problems by simulating how quantum systems settle into low-energy states. By allowing a system to tunnel between different possible configurations, it can escape local energy minima and find better solutions. Companies like D-Wave use quantum annealing machines based on superconducting qubits, where tunneling is fundamental to operation. There's even a class of materials called Josephson junctions used in superconducting circuits. A Josephson junction consists of 2 superconductors separated by a thin insulating barrier. Because of tunneling, a supercurrent can pass through without voltage. This is the Josephson effect. It enables ultra-sensitive magnetic field detectors called SQUIDs, superconducting quantum interference devices. They detect changes in magnetic flux 1 billion times smaller than Earth's magnetic field, all thanks to tunneling. So how do we calculate the tunneling probability? Quantum mechanics provides solutions to the Schrödinger equation for potential barriers. In the simple case of a rectangular barrier, the probability of tunneling decreases exponentially with the width and height of the barrier. More precisely, tunneling probability is proportional to the exponential of -2 times the square root of twice the particle's mass times the difference between the barrier height and particle energy times the barrier width, all divided by Planck's constant. This is why tunneling is significant only on atomic or subatomic scales. The probability drops drastically for larger particles or thicker barriers, but it is never zero, and that's the key. Quantum mechanics allows the improbable, not the impossible. And at small enough scales, the improbable becomes common. We build devices on this principle. We explain nature with this principle. Tunneling is not a failure of physics. It is physics refined to the deepest level we know. Particles do not ask permission. They follow probabilities. And in that uncertainty lies a strange kind of certainty, a universe that is soft at the edges, fuzzy in the details, and more connected than classical thought allowed. Tunneling breaks walls, not with force, but with probability, and it reminds us there are ways through we don't yet understand. Chapter 16. The structure of the atom, and the forces that bind it. Every object around you, your hands, the chair, the air, is made from atoms. These atoms are not indivisible. They are complex structures governed by fundamental forces, arranged in patterns that define the behavior of all matter. An atom consists of a nucleus, containing protons and neutrons, surrounded by electrons that exist in probabilistic clouds, not neat orbits. Let's start with the nucleus. At the center of every atom, the nucleus holds almost all its mass. Protons carry a positive electric charge, neutrons carry no charge, but both contribute to the atomic mass. The number of protons in the nucleus defines the element. Hydrogen has 1, helium has 2, carbon has 6, gold has 79. This number is called the atomic number. It determines the atom's identity and its position on the periodic table. Protons repel each other because like charges push apart. So why does the nucleus hold together? The answer is the strong nuclear force. This is one of the 4 fundamental forces of nature, the others being electromagnetism, gravity, and the weak nuclear force. The strong force is the most powerful of them all, but it acts only at very short distances, a few femtometers across. That's quadrillionths of a meter. It binds protons and neutrons together, overcoming the electromagnetic repulsion of the positively charged protons. Without the strong force, nuclei would fly apart. Atoms would not exist. Neutrons play a stabilizing role. They contribute to the strong force binding, but do not add to the repulsive electric charge. This is why isotopes exist. Atoms of the same element, with different numbers of neutrons. Some isotopes are stable, others are not. Unstable isotopes decay over time, emitting radiation as they seek a lower energy state. This decay is governed by the weak nuclear force, the short-range force responsible for processes like beta decay, where a neutron transforms into a proton, releasing an electron and a neutrino. The weak force, though less familiar, plays a crucial role in the sun's fusion processes and in the transformation of elements in stars. Now, beyond the nucleus lie the electrons. Electrons are elementary particles with negative charge and almost no mass compared to protons and neutrons. In classical models, electrons orbited the nucleus like planets, but quantum mechanics replaced that picture. Electrons exist in orbitals, regions of space where they are most likely to be found. These orbitals have shapes, spherical, dumbbell, and more governed by solutions to the Schrödinger equation. Each electron orbital is defined by quantum numbers. There's the principal quantum number, which describes the energy level, the angular momentum number, which defines shape, the magnetic number defining orientation, and the spin quantum number, which gives the electron an intrinsic angular momentum. No 2 electrons in an atom can share the same set of quantum numbers. This is the Pauli exclusion principle. It explains the structure of the periodic table and why elements form specific bonds. Chemical properties arise from how atoms share or transfer electrons. When atoms bond, their outer electrons, called valence electrons, interact to create molecules. There are different types of bonds: covalent bonds where electrons are shared, ionic bonds where electrons are transferred, creating charged ions, metallic bonds where electrons are delocalized across many atoms. These bonds are not static. They involve constant quantum interactions, fields, forces, probabilities. Let's look deeper. Protons and neutrons themselves are not fundamental. They are made of quarks, elementary particles that come in types called flavors: up, down, strange, charm, top, and bottom. A proton consists of 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. These quarks are held together by the strong interaction mediated by particles called gluons. Gluons are massless carriers of the strong force. They constantly exchange between quarks, binding them tightly. Unlike gravity and electromagnetism, the strong force becomes stronger as quarks are pulled apart. This phenomenon is called confinement. It means you cannot isolate a single quark. Trying to pull one free creates enough energy to generate new quark pairs, so they remain in groups. This is why we never observe free quarks. We only see bound states, like protons, neutrons, and mesons. Electrons, on the other hand, are fundamental. They belong to a family called leptons. They are not made of smaller parts. The interaction between electrons and protons is governed by electromagnetism, mediated by photons, the carriers of the electromagnetic force. The electromagnetic force is long-range, unlike the strong and weak forces. It is responsible for nearly all chemistry, light, electricity, and magnetism. Gravity, the weakest force, also acts on atoms, but it's negligible compared to the other 3. Yet over large scales, gravity dominates, shaping stars, galaxies, and the universe. Atoms are mostly empty space. If the nucleus were the size of a peanut, the electron cloud would stretch hundreds of meters away. But this space isn't truly empty. It's filled with quantum fields, fluctuations, and virtual particles. The Heisenberg uncertainty principle tells us that we cannot simultaneously know both the exact position and momentum of a particle. This uncertainty is not due to measurement error. It is a fundamental property of quantum systems. The atom is a delicate balance of attractive and repulsive forces, of probability and energy, of particles and fields. It obeys strict mathematical rules, yet remains unpredictable in its details. Understanding atoms has led to modern technology: lasers, semiconductors, nuclear energy, MRI machines, quantum sensors, and still new models evolve. Quantum electrodynamics, QED, describes how electrons and photons interact. It is one of the most accurate theories ever tested. Quantum chromodynamics, QCD, deals with quarks and gluons, governing the strong force. The standard model of particle physics combines these forces, strong, weak, and electromagnetic, into a unified framework. It describes all known fundamental particles and their interactions, except gravity. Gravity remains outside the standard model. A complete theory of everything, a quantum theory of gravity, is still being sought. Proposals include string theory and loop quantum gravity, but the atom, though small, still holds secrets that challenge the biggest questions. At its heart, the atom is not solid. It is a dynamic, probabilistic structure held together by invisible interactions. It reminds us that matter is not what it seems, that the universe is built from uncertainty, governed by forces we can name, but barely visualize. And within every atom in your body, your voice, your thoughts, is a piece of the universe's original energy, still bound, still dancing. Chapter 17. Electromagnetism and the unification of light and force. Every time you switch on a light, use your phone, or feel the warmth of the sun, you are interacting with one of the 4 fundamental forces of nature: electromagnetism. It governs the behavior of charged particles, the structure of atoms, the color of the sky, and the functioning of every electrical device you've ever used. At its core, electromagnetism is the unification of electric and magnetic fields into a single force. This force acts between particles with electric charge. It operates over infinite distances, though its strength decreases with the square of the distance. Electricity and magnetism were once considered separate phenomena. Electric fields were thought to arise from static charges. Magnetic fields were associated with moving charges or currents. But in the 19th century, James Clerk Maxwell formulated a set of equations that showed how electric and magnetic fields are interlinked, how one can give rise to the other. These are Maxwell's equations, 4 elegant statements that describe how charges and fields interact. They are the foundation of classical electromagnetism, optics, and modern electrical engineering. The first is Gauss's law, which states that electric charges produce electric fields, and the total flux of the electric field through a closed surface is proportional to the enclosed charge. The second is Gauss's law for magnetism, which states that there are no magnetic monopoles, no isolated north or south poles. Magnetic field lines always form closed loops. The third is Faraday's law of induction, which states that a changing magnetic field induces an electric field. This principle powers electric generators and transformers. The fourth is Ampere's law with Maxwell's correction, which states that magnetic fields are generated by electric currents and by changing electric fields. Together, these equations imply that light itself is an electromagnetic wave, a self-propagating disturbance of electric and magnetic fields. In empty space, this wave travels at a speed determined by the permittivity and permeability of the vacuum. This speed, roughly 300,000 kilometers per second, is the speed of light. That light is an electromagnetic wave was a revolutionary insight. It meant that visible light, radio waves, X-rays and gamma rays are all the same kind of thing, just different frequencies of the electromagnetic spectrum. The electromagnetic spectrum spans a vast range. Radio waves have the longest wavelengths and the lowest frequencies. Then come microwaves, infrared, visible light, ultraviolet, X-rays, and finally gamma rays, which have the shortest wavelengths and the highest energies. Each region of the spectrum interacts differently with matter. Infrared is absorbed as heat. Ultraviolet can break molecular bonds. X-rays penetrate soft tissue but not bone. Gamma rays can disrupt DNA and are emitted by nuclear reactions. The visible spectrum, what your eyes can detect, ranges from red to violet. Red light has longer wavelengths and lower energy. Violet has shorter wavelengths and higher energy. Why the sky is blue? Because shorter wavelengths of sunlight scatter more in the atmosphere. This is known as Rayleigh scattering. Why sunsets are red? Because the sun's light must pass through more atmosphere at dusk, scattering away the shorter blue wavelengths and leaving the longer red ones. Electromagnetic waves do not require a medium. Unlike sound or water waves, they can travel through the vacuum of space. This is why sunlight reaches Earth across 93 million miles of emptiness. At the particle level, electromagnetic interaction is mediated by photons, massless particles that carry electromagnetic force. When two electrons repel each other, they are exchanging virtual photons. These photons are not directly observable, but their effects are measurable. The strength of the electromagnetic interaction depends on the electric charge of the particles and the inverse square of the distance between them. It is vastly stronger than gravity at small scales, roughly 10 to the power of 36 times stronger, yet we notice gravity more because electromagnetic forces often cancel out in macroscopic objects. Your body contains equal numbers of positive and negative charges, so does the Earth. That's why you don't feel an electric pull toward the ground. Electrons are bound to atomic okonoike by the electromagnetic force. They exist in quantized energy levels, and when they jump from one level to another, they emit or absorb photons of specific energies. This explains atomic spectra, the unique fingerprints of elements. Each element emits light at particular wavelengths due to electron transitions. This is how we identify the composition of distant stars. By analyzing the light they emit, we can determine which elements are present, even across billions of light years. Electromagnetic radiation also carries momentum. Light can exert pressure. This radiation pressure is weak, but measurable, and is being used in the design of solar sail spacecraft that propel themselves using sunlight. The theory that unified electricity, magnetism, and light was just the beginning. Later came quantum electrodynamics, or QED. QED is the quantum theory of the electromagnetic force. It describes how photons interact with charged particles, accounting for probabilities, virtual particles, and higher-order corrections. It is one of the most accurate physical theories ever developed. Its predictions agree with experiments to more than 10 decimal places. Feynman diagrams developed by Richard Feynman are visual tools for calculating particle interactions in QED. They depict paths of electrons, positrons, and photons, with vertices representing interactions. These diagrams simplify complex integrals into manageable computations. Electric fields point from positive to negative charge. Magnetic fields form closed loops. Changing one creates the other. This mutual creation is why electromagnetic waves are self-sustaining. Electric creates magnetic, magnetic creates electric, and the wave moves forward. Electric currents generate magnetic fields. This is the basis of electromagnets, motors, and transformers. Magnetic fields affect moving charges. This is the Lorentz force, a key principle behind cyclotrons and mass spectrometers. The unification of electricity and magnetism was a major milestone. It showed that forces we once thought separate are manifestations of a deeper unity. Later, the electroweak theory unified electromagnetism with the weak nuclear force. At high energies, these two forces become indistinguishable. This unification was confirmed in the 1970s through experiments at particle accelerators. It led to the development of the Standard Model of Particle Physics, a framework that describes all known matter and its interactions, except gravity. The search continues for a grand unified theory, a model that merges all forces, possibly including gravity. In technology, electromagnetism powers civilization. Generators convert mechanical energy into electrical energy through magnetic induction. Electric motors do the reverse, converting electrical energy into motion. Transistors, the building blocks of modern electronics, manipulate electric currents using semiconductor materials and electromagnetic principles. Fiber optics use total internal reflection to guide light over long distances, transmitting data at nearly light speed. Wireless communication uses radio waves, microwaves, and infrared to transmit signals from mobile phones to satellites. Electromagnetic radiation is also used in medicine. X-rays create images of bones. MRI machines use radio waves and magnetic fields to scan soft tissue. Even microwave ovens heat food by agitating water molecules with electromagnetic waves. The electromagnetic force is not just a scientific curiosity, it is essential to life, technology, and the cosmos. Your neurons fire using electrical impulses. Your vision depends on photon detection. Your sense of warmth comes from infrared absorption. From atoms to galaxies, from circuits to stars, electromagnetism shapes the universe. And at the deepest level, it reveals that energy, light, and force are facets of the same reality. A field, a wave, a particle, all at once. Chapter 18. The Fabric of Spacetime and Einstein's General Relativity. What if space isn't just emptiness? What if time isn't just a ticking clock? Einstein's theory of general relativity tells us that space and time are not separate. They are woven together into a single entity, spacetime. And this fabric curves in response to mass and energy. General relativity replaced the Newtonian idea of gravity as a force with a new understanding. Mass tells spacetime how to curve, and spacetime tells mass how to move. In Newton's world, gravity was instantaneous, a force acting at a distance. In Einstein's world, gravity is geometry, a curvature in the fabric of the universe. Imagine a heavy ball placed on a stretched rubber sheet. The sheet curves around it. A marble rolling nearby will follow that curvature, not because of an invisible force, but because the shortest path is now bent. That's how general relativity describes planetary motion. The Earth orbits the Sun not because it's being pulled, but because the Sun curves spacetime, and the Earth moves along the curved path. This idea came from a simple thought experiment. Einstein imagined falling in an elevator. Inside, you would feel weightless, the same feeling astronauts have in orbit. This led to the principle of equivalence, that acceleration and gravity are locally indistinguishable. From this, the theory of general relativity emerged. Einstein published it in 1915. It included a set of 10 field equations, describing how matter and energy influence the curvature of spacetime. These equations are complex. They relate the geometry of spacetime described by tensors to the distribution of mass and energy. One solution to these equations predicted a phenomenon that had never been observed: the bending of starlight by gravity. In 1919, during a total solar eclipse, Sir Arthur Eddington confirmed this effect. Starlight passing near the Sun was bent, exactly as Einstein predicted. This was the first direct confirmation that gravity affects the path of light, and it made Einstein a global icon. General relativity also predicts time dilation. Time runs slower in stronger gravitational fields. This isn't just theory, it's been tested and confirmed. For example, atomic clocks flown in airplanes tick slightly faster than identical clocks on the ground, and clocks on GPS satellites must be adjusted for both special and general relativistic effects to remain accurate. Without this adjustment, GPS positioning would drift by kilometers each day. Your phone navigation would be useless without general relativity. The theory also predicts the precession of planetary orbits. Mercury's orbit doesn't close perfectly with each revolution. There's a small shift, or precession, that Newtonian mechanics couldn't fully explain. General relativity accounts for the discrepancy with precise accuracy. But perhaps the most extraordinary prediction is the existence of black holes. These are regions where space-time curvature becomes extreme, where gravity is so intense that not even light can escape. At the center of a black hole is a singularity, a point of infinite density and zero volume, where our known laws of physics break down. Surrounding the singularity is the event horizon, a boundary beyond which nothing can return. It is not a physical surface, but a point of no return in space-time. Black holes were once thought to be purely theoretical. Now, we know they are real. We have detected their presence through the gravitational effects on nearby stars, and more recently, through gravitational waves. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected ripples in spacetime caused by two black holes merging. This confirmed another major prediction of general relativity, that accelerating masses produce gravitational waves. Gravitational waves stretch and squeeze spacetime itself. They travel at the speed of light and carry information about cataclysmic events in the universe. LIGO's detection required measuring distances smaller than the width of a proton. It was one of the most sensitive experiments in history. And in 2019, the Event Horizon Telescope produced the first image of a black hole's shadow. It confirmed predictions from relativity about the way light bends near the event horizon. Black holes aren't the only strange result. General relativity also allows for the concept of wormholes, tunnels in spacetime that could, in theory, connect to distant regions of the universe. These are solutions to the Einstein field equations, but remain purely speculative. They would require exotic matter with negative energy density to remain open. Similarly, closed time-like curves suggest the possibility of time travel within certain solutions to the equations. But again, these remain mathematical curiosities, not experimentally verified phenomena. Another major application of general relativity is in cosmology, the study of the universe's large-scale structure. Einstein's equations describe how the universe evolves over time. In fact, the equations suggested that the universe could not be static, it must be expanding or contracting. Einstein initially resisted this idea. He added a term called the cosmological constant to force a static universe. But in 1929, Edwin Hubble discovered that galaxies are moving away from us. The universe is expanding. Einstein later called the cosmological constant his biggest blunder. Ironically, the term has returned to modern physics as a possible explanation for dark energy, the mysterious force driving the accelerated expansion of the universe. General relativity predicts that the universe began from a singularity, an infinitely dense point about 13.8 billion years ago. This is the Big Bang model. It's supported by multiple lines of evidence: the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of galaxies. Over time, general relativity has passed every experimental test thrown at it, from the deflection of light, to gravitational redshift, to time dilation and orbit precession. Its predictions have proven precise and consistent. But despite its successes, general relativity does not explain everything. It breaks down at quantum scales. It doesn't incorporate the principles of quantum mechanics. Physicists have long sought a quantum theory of gravity, a framework that unifies general relativity with quantum physics. Approaches include string theory, which posits that particles are tiny vibrating strings, and loop quantum gravity, which models spacetime itself as quantized. Neither theory has been confirmed, but both aim to reconcile the geometric view of spacetime with the probabilistic world of quantum fields. Until then, general relativity remains our best description of gravity in the cosmos. It shows that space can stretch, bend, twist, that time is not absolute, that gravity is not a force, but a manifestation of curvature, and that the universe is far more flexible, far more dynamic than anyone imagined before 1915. The planets orbit not because they are pulled, but because they move through curved spacetime. Light bends around stars not because it has mass, but because spacetime tells it how to travel. This is the beauty of general relativity. It transforms gravity from a mechanical force into a property of geometry, and it opens the door to understanding time, black holes, the universe, not as fixed structures, but as flowing, evolving, curved realities. A single theory reshaped our view of everything we thought was fixed and flat. Chapter 19. Time dilation and the paradoxes of relativity. What if time is not absolute? What if two people, both looking at clocks, measure two different durations for the same event. This is not just theory. It's a consequence of Einstein's special relativity, and it's a real measurable part of our universe. Time dilation is the idea that time passes at different rates depending on an object's speed or its position in a gravitational field. It breaks the notion of a universal clock. Instead, every observer carries their own version of time. Let's begin with special relativity, Einstein's theory from 1905. It deals with observers moving at constant velocities without acceleration or gravity. Two fundamental postulates form the basis. First, the laws of physics are the same in all inertial frames, that is, frames moving at constant velocity. Second, the speed of light in a vacuum is constant for all observers regardless of their motion. This leads to surprising results. If one person is standing still and another is traveling close to the speed of light, they will experience time differently. To understand this, imagine a light clock. It consists of two mirrors with a beam of light bouncing between them. For someone at rest relative to the clock, the light travels vertically up and down, but for someone moving alongside the clock, the light follows a diagonal path. Because the mirrors are also moving horizontally, since the speed of light must be the same for both observers, the light must take longer to travel the diagonal path. This means time must slow down for the moving observer. This is time dilation. It's not an illusion, it's real, and it's been tested. Muons, subatomic particles created in the upper atmosphere, should decay before reaching Earth. Their half-life is about 2 microseconds, but many are detected at sea level. Why? Because they travel near the speed of light. From our perspective, their internal clocks tick more slowly. This gives them more time to reach Earth. We've also tested time dilation with airplanes. Atomic clocks flown around the world return ticking slightly behind identical clocks left on the ground. Even at commercial jet speeds, the effect is measurable. In particle accelerators, fast-moving particles have longer lifetimes than their stationary counterparts. This matches the predictions of relativity exactly. But time dilation isn't just about motion. It also happens in gravity. This is described by general relativity, Einstein's later theory from 1915. The stronger the gravitational field, the slower time passes. This has been observed using extremely precise clocks. Clocks placed at different altitudes tick at different rates. A clock on a mountaintop ticks slightly faster than one at sea level. This is gravitational time dilation. It's why GPS satellites must correct their internal clocks. They're farther from Earth's mass, so time moves faster for them than it does for receivers on the ground. Without these adjustments, GPS systems would be inaccurate by kilometers in just a single day. Both kinds of time dilation due to motion and gravity are deeply verified. They are not errors or illusions, they are how time truly behaves. Now let's explore some of the strange implications. Consider the twin paradox. Imagine two identical twins. One stays on Earth, the other travels on a spaceship, close to the speed of light, then returns. From the perspective of the traveling twin, time slows down on Earth, but from the Earth-bound twin's view, the traveler is the one moving, and their clock should run slower. This seems symmetrical, so who actually ages less? The resolution lies in acceleration. The traveling twin must turn around, accelerate, and decelerate. This breaks the symmetry. Special relativity applies only in constant motion. Once acceleration enters, general relativity is needed, and that shows the traveling twin does indeed age less. This isn't just a thought experiment. In principle, such a journey would result in real, measurable age difference. Let's say the traveler goes to a star system 10 light-years away at 99.5% the speed of light. From Earth's frame, the round trip takes about 20 years, but for the traveler, only a few years pass due to time dilation. When they return, their twin has aged 2 decades, but they have aged much less. This is not science fiction. It's embedded in the mathematics of space-time. Another consequence is length contraction. Objects moving near the speed of light appear shorter along the direction of motion. If you travel fast enough, the distance to your destination contracts. From your frame, you're moving a shorter distance in less time. So both time dilation and length contraction work together to preserve the constancy of light speed. Now, consider simultaneity. In classical physics, if two events happen at the same time, they are simultaneous for all observers. But relativity changes this. Simultaneity is relative. Two events that appear simultaneous to one observer may not be simultaneous to another moving observer. This is due to the relativity of simultaneity. a core concept in Einstein's theory. There's no absolute now that spans the universe. What you call now depends on how fast you are moving and in what direction. This has deep implications for causality and physics. It means there's no universal present, just a web of overlapping timelines, each defined by an observer's motion. Special relativity also introduces the space-time interval. This is a quantity that combines space and time into a single, invariant measurement. No matter how you move, the space-time interval between two events remains constant. This unifies space and time into a single geometry. The geometry of space-time is described by Minkowski space. It treats time as a fourth dimension, but with a crucial difference. It behaves differently than the three spatial dimensions. In space-time diagrams, time is often plotted vertically, while space runs horizontally. The path of a light beam forms a diagonal line at 45 degrees. Anything moving slower than light must follow a path within this light cone. This preserves causality. Effects cannot precede causes. Faster than light travel, if possible, would break this causal structure. And yet, relativity doesn't forbid strange paths through spacetime. Solutions like closed time-like curves suggest possible loops in time, where an object could return to its own past. These require exotic conditions, like spinning black holes or wormholes, and remain theoretical. So far, no violations of causality have been observed in nature. Back to time dilation. What happens near a black hole? Close to the event horizon, gravity becomes extreme. Time slows dramatically. To a distant observer, a falling object appears to freeze at the horizon, its clock slowing to a stop. But from the object's own frame, time continues normally. They pass the horizon in finite time, unaware of the cirrus freezing. This gravitational time dilation creates a natural time barrier. The movie Interstellar used this idea. A planet near a black hole, where 1 hour equals 7 years elsewhere. Though exaggerated, the concept is based on real physics. In our daily lives, these relativistic effects are small, but they become critical in high-speed travel, astronomical observations, and advanced technology. Modern physics accepts that time is not fixed. It stretches and contracts based on speed and gravity. It is not universal. It is personal. It is local to each frame of reference. The deeper we study time, the more we discover it's not a background stage, but an active player in the dynamics of reality. Einstein gave us the tools to understand this, but even he admitted that the nature of time remains one of the deepest mysteries. Chapter 20. The Quest for a Theory of Everything. We can describe how stars form, how gravity curves space-time, how atoms bind, and how particles interact. But even now, after centuries of discovery, there is no single equation that ties it all together, no ultimate blueprint that explains every force, every particle, every pattern of existence. This is the goal of the theory of everything, a framework that unites all known physical laws into one coherent, consistent model. Right now, physics is divided. On one side stands quantum mechanics, ruling over the very small atoms, particles, fields. On the other stands general relativity, ruling over the very large stars, galaxies, black holes, space-time. Each theory is stunningly successful in its own domain, but they do not speak the same language. Their mathematical foundations clash. Quantum mechanics is probabilistic. It describes uncertainties and waves of possibility. Particles are represented by wave functions. They exist in superpositions, being here and there, until a measurement collapses the wave. General relativity, on the other hand, is deterministic. It treats spacetime as a smooth fabric. Mass and energy curve this fabric, dictating the motion of planets, light, and time itself. But when both gravity and quantum effects are significant, such as near black hole singularities or in the earliest moments of the Big Bang, neither theory is sufficient. We need a new framework, one that combines quantum mechanics with gravity. This is what physicists call quantum gravity. Several approaches aim to bridge the gap. Each has its strengths, challenges, and mysteries. One of the most well-known is string theory. It proposes that particles are not point-like, but are tiny vibrating strings. Different vibration patterns give rise to different particles. An electron is one vibration mode, a photon is another. All particles and forces emerge from string-like motion. String theory also naturally includes gravity. One of the string's vibration modes behaves like a graviton, a hypothetical quantum particle that mediates gravity. But for the mathematics to work, string theory requires more than 3 dimensions of space. It needs 9 spatial dimensions and 1 of time. Where are the extra dimensions? They may be compactified, curled up at scales too small to detect, like threads tightly woven into a larger fabric. String theory also led to the idea of brains, multi-dimensional objects on which strings can end. Our universe could be a 4-dimensional brain floating in a higher dimensional space. Though elegant, string theory lacks experimental confirmation. It produces many possible universes, each with different physical laws. This vast collection is known as the string landscape. Some physicists see this as a problem. Others suggest it may explain the fine-tuning of our universe. Another approach is loop quantum gravity. It attempts to quantize space-time directly, not as a smooth fabric, but as a network of discrete loops. These loops are tiny, on the scale of the Planck length, about 10 to the minus 35 meters. They form a spin network, a kind of scaffolding from which space and geometry emerge. In loop quantum gravity, area and volume are quantized. Space-time itself has a granular structure, like pixels on a screen. This theory preserves the principles of general relativity while incorporating quantum rules. It also offers potential explanations for black hole entropy and singularity avoidance. Yet, like string theory, loop quantum gravity has not yet yielded direct predictions that can be tested with current technology. Some physicists explore causal dynamical triangulations, asymptotic safety, emergent gravity, and non-commutative geometry, each have a path toward the same summit. There is also supersymmetry, a proposed symmetry between matter and force particles. It predicts a partner particle for every known particle. If true, it would resolve several inconsistencies including the hierarchy problem and may aid in unifying the forces. The standard model of particle physics already unifies the electromagnetic, weak and strong nuclear forces, but gravity stands apart. Physicists dream of embedding all 4 forces into a grand unified theory. The theory of everything would go further, explaining not only interactions, but the origin of space, time, and quantum behavior itself. Why do particles have the masses they do? Why does the speed of light have its specific value? Why is the universe made of matter and not antimatter? The ultimate theory would not just describe these features, it would explain why they could not be otherwise. To reach it, we need more than equations, we need data. The Large Hadron Collider at CERN discovered the Higgs boson in 2012, confirming the mechanism by which particles acquire mass. But it has not yet revealed supersymmetry or extra dimensions. Future colliders, precision experiments, and new observations may provide the needed breakthroughs. Some physicists look to the early universe. The cosmic microwave background contains subtle patterns that may reveal quantum gravitational effects. Others study black hole thermodynamics. Stephen Hawking showed that black holes emit radiation now called Hawking radiation, and have entropy proportional to the area of their event horizon. This suggests a deep link between gravity, quantum mechanics, and thermodynamics. A black hole appears to destroy information, but quantum theory forbids that. Resolving this information paradox may lead us to new physics. There are even attempts to rethink the foundations. What if space-time is not fundamental? What if it emerges from a more basic, information-based structure? This leads to holography. The holographic principle suggests that the information inside a volume of space can be described by data on its boundary. In this view, our 3-dimensional world may be a projection from a 2-dimensional surface. It sounds fantastical, yet it arises naturally in certain theories of quantum gravity. One version, known as AD-SCFT correspondence, proposes a duality between a gravitational theory in a curved space and a quantum field theory without gravity on its boundary. This correspondence is a powerful tool, not a final theory, but a guidepost showing how gravity and quantum physics might be 2 sides of the same coin. Still, challenges remain. There is no experimental test of holographic duality in our universe's geometry. And yet, the pursuit continues. Physics has always advanced by unifying what once seemed separate. Electricity and magnetism were unified into electromagnetism. Electromagnetism and the weak force were unified in the electroweak theory. Each unification revealed deeper simplicity beneath apparent complexity. So it is with the theory of everything. It may not come in one step, but through layers of insight, whether through strings, loops, or something yet unimagined. The goal is the same, a complete, self-consistent understanding of reality. Not just how particles move, but why they exist. Not just how space expands, but why it began. This journey is about more than physics. It is about meaning. It is about asking the most human of questions. What is everything? Science may never find the final answer, or perhaps it already has part of it, hidden in equations yet to be interpreted. The universe is not silent. It speaks in patterns, in symmetry, in structure. Our task is to listen. Chapter 21. Chaos Theory and the Mathematics of Unpredictability. There are patterns in nature, spirals in galaxies, branching in trees, the ripples of sand dunes and the curling of smoke. Yet underneath these patterns lies something more complex. A truth that even systems governed by simple rules can behave unpredictably. This is the realm of chaos theory. It is not randomness. It is not disorder. It is a form of order that appears disordered. A structure so sensitive, so interconnected, that small changes can lead to wildly different outcomes. The key phrase is sensitive dependence on initial conditions, a phrase often illustrated by the so-called butterfly effect. The idea is this: a butterfly flaps its wings in Brazil, and weeks later, a tornado forms in Texas. This may sound poetic, but it's based on mathematics. In 1961, meteorologist Edward Lorenz discovered this sensitivity while working with a weather simulation. He entered numbers into a computer model, and later ran it again, rounding just one variable slightly differently. To his surprise, the outcome was completely different, not slightly altered, completely transformed. The system was deterministic, there was no randomness. Yet tiny changes in the starting conditions led to drastic shifts in behavior. This was the beginning of chaos theory. It showed that even systems with clear, defined equations could become unpredictable over time. Weather is one example. It obeys the laws of fluid dynamics and thermodynamics. But due to the complexity and sensitivity, its long-term behavior becomes chaotic. The equations are known, the Navier-Stokes equations, describing the flow of fluids, but solving them exactly for a large system like the atmosphere is nearly impossible. Small changes in temperature or pressure can grow exponentially. This is why weather forecasts are reliable only for a few days ahead. Beyond that, the chaos makes prediction unstable. But chaos theory isn't just about weather. It applies to many systems, from planetary motion to the dripping of a faucet. Take the double pendulum, a pendulum with another pendulum attached to its end. It seems simple, but its motion becomes erratic and sensitive. Even with precise starting conditions, its path becomes wildly unpredictable after a few swings. And yet, if you graph the motion, you find patterns. Not order in the classical sense, but structure in the chaos. This structure is often fractal. Fractals are shapes that repeat at every scale. They are self-similar. A small part looks like the whole. Zoom in and you see the same shape reappearing. One famous example is the Mandelbrot set, a set of complex numbers that generates a beautiful infinite pattern. Its boundary is endlessly detailed. No matter how far you zoom in, new structures emerge. This isn't just mathematical art. Fractals appear in nature in coastlines, mountain ranges, snowflakes and blood vessels. Chaos and fractals are linked. Chaotic systems often display fractal structure in the space of possible states, what physicists call phase space. Phase space is a way to visualize a system's behavior. Each point represents a possible state, a combination of positions and velocities. In chaotic systems, the path through phase space traces out a complex shape called a strange attractor. It is not random, but it never repeats exactly. It is bounded, yet infinite in complexity. One of the most studied is the Lorenz attractor. It looks like a butterfly with two wings, a looping, swirling structure representing the evolution of a weather model. You can never predict exactly where the system will go, but you can describe the shape it stays within. This is the heart of chaos. Predictable bounds, but unpredictable trajectories. This kind of behavior shows up in economics, biology, ecology, and even the motion of Saturn's moons. In the heart, the rhythm of beats is not perfectly regular. It has chaotic features, not noise but complexity. In population biology, predator-prey models like the Lotka-Volterra equations can enter chaotic regimes, depending on growth rates and interaction terms. Even the orbits of planets, once thought to be completely stable, can show chaotic interactions over long time scales. In the late 20th century, mathematicians studied the three-body problem, how three gravitationally interacting objects move over time, the system becomes chaotic, resisting neat predictions. Sometimes a small moon can destabilize the orbits of two larger bodies. Still, not all chaos is disorder. Within chaos, there is coherence. The field of nonlinear dynamics studies these systems, how small inputs can create massive effects, and how feedback loops shape behavior. This contrasts with linear systems, where outputs are proportional to inputs and effects are easy to sum. Nonlinear systems are the norm in nature. They feature feedback thresholds and multiple outcomes. One tiny input, at the right moment, can tip a complex system into a whole new regime. That's how avalanches happen. A single snowflake lands on an unstable slope, and the entire hillside shifts. Not because the snowflake was powerful, but because the system was ready to respond. In ecosystems, removing a single species can collapse entire food webs. In climate science, feedback loops involving ice, ocean currents and carbon can push the system toward tipping points. These thresholds are not obvious. They lie hidden in the interactions. The study of chaos helps identify these thresholds and how small interventions might prevent large disruptions. This also applies in engineering. Power grids, internet traffic, supply chains, all are nonlinear systems prone to cascading failures. Chaos theory provides tools to model, stabilize, and understand them. It teaches us humility that even when rules are known, outcomes may not be. But it also shows beauty, that the universe is not rigid, but dynamic, full of sensitivity and emergence. Patterns emerge from chaos, but not through control, through evolution, adaptation, and feedback. This perspective reshapes how we see everything, that life, the brain, the weather, the economy are not clockwork machines, but sensitive, shifting landscapes. Chaos theory bridges disciplines. It's not just a branch of math, it's a lens through which to see complexity. Even in quantum mechanics, chaos plays a role. While quantum systems are inherently probabilistic, there is a growing field called quantum chaos, which explores how classical chaos emerges from quantum rules. This includes how wave functions evolve in chaotic potentials, and how randomness connects to entropy and measurement. Entropy, in fact, is another thread that ties into chaos. It measures disorder, but also the number of possible configurations. As systems evolve, they move from low entropy to high entropy, from order to disorder. But in chaotic systems, this disorder has form. The weather may be unpredictable, but it follows rules. And those rules reveal fractal patterns in storms, clouds, and currents. The study of turbulence, the swirling, chaotic motion of fluids, remains one of the great unsolved problems in physics. Despite centuries of study, we still lack a complete theory of turbulence. It is chaotic, fractal, and sensitive to scale and structure. Chaos theory offers a way forward, not to eliminate unpredictability, but to embrace and understand it. To see that behind every wave, every heartbeat, every tree branch, lies mathematics that is both subtle and deep, and that sometimes the most surprising truths come from the systems we thought we understood. Chapter 22: Crystallography and the Hidden Symmetry of Matter. Look closely at a snowflake. Its six-fold symmetry is not accidental. It is the result of atomic patterns repeating again and again, a reflection of deeper rules guiding matter. This is the world of crystallography, the science of studying the structure of crystals, solids whose atoms are arranged in a regular, repeating pattern. Crystals are more than gemstones. They are found in salt, metals, ice, and even the bones in your body. They are everywhere, shaping the world with unseen mathematical order. At the heart of crystallography is the idea of symmetry. Symmetry means that an object looks the same when you rotate, reflect, or shift it. In crystals, symmetry governs how atoms fit together. To build a crystal, atoms assemble into unit cells, the smallest repeating structure that tiles space. Just like a tile on a floor, a unit cell repeats in 3 dimensions to form a complete lattice. There are only 7 crystal systems in 3-dimensional space. These include cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. Each system defines a family of possible unit cell shapes. For example, the cubic system includes the simple cube, where atoms sit at each corner of a cube and repeat outward. Diamond, salt, and many metals crystallize in cubic forms. These structures are not guessed. They are discovered using X-ray diffraction. When X-rays strike a crystal, they bounce off the layers of atoms and interfere with each other. The pattern of interference, called a diffraction pattern, encodes information about the atomic layout. Using these patterns, scientists can reconstruct the exact positions of atoms within a crystal. This is how the structure of DNA was first revealed. In 1953, Rosalind Franklin's X-ray diffraction images allowed Watson and Crick to deduce the double helix. Without crystallography, the molecular code of life would have remained hidden. Crystallography is not just for biology. It has revealed the atomic arrangements in thousands of compounds, from semiconductors to enzymes to superconductors. Each crystal's symmetry determines its properties. How it bends light, conducts electricity, or resists heat, all depend on how atoms are packed inside. Even imperfections called crystal defects can have profound effects. For example, in silicon chips, small impurities known as dopants are deliberately introduced into the crystal to control how electricity flows. In metals, dislocations in the crystal lattice allow them to bend without breaking. In snowflakes, slight temperature changes alter how water molecules freeze, leading to endless varieties, each built on the same six-fold symmetry. Not all crystals are perfect repeats. Some structures exhibit quasicrystals, patterns that fill space but never repeat exactly. They have order but not periodicity. This was once thought impossible, but in 1982, Dan Shechtman discovered a metal alloy with five-fold symmetry, something forbidden in traditional crystallography. This led to a revolution. Quasicrystals were accepted, and Shechtman won the Nobel Prize in Chemistry in 2011. Quasicrystals are real, and they appear in nature, even in meteorites. Their atomic structure resembles Penrose tilings, a set of non-repeating tiles that still cover a plane completely. This discovery blurred the line between mathematics and matter. It showed that the rules of atomic assembly were more flexible and surprising than once believed. Crystallography also intersects with solid-state physics. Electrons moving through a crystal experience the periodic potential of the lattice. This leads to the formation of energy bands. These bands determine whether a material is a conductor, a semiconductor, or an insulator. In a conductor like copper, electrons can move freely through the bands. In insulators, the bands are full and electrons cannot jump to higher levels without added energy. Semiconductors sit between these two. They form the foundation of modern electronics. The precise arrangement of atoms can tune a crystal's electrical, thermal, and optical properties. Crystals can even change how light behaves. In photonic crystals, the structure blocks certain wavelengths of light, much like electrons are blocked by energy bands. These materials can guide light, bend it, or trap it, leading to advances in fiber optics and sensors. Nature uses these tricks too. The vivid blue of a butterfly wing comes not from pigment, but from the microscopic crystal structure of its scales. These natural structural colors are vivid, iridescent, and long-lasting, because they depend on geometry, not chemistry. Crystallography also helps identify minerals. Each mineral has a unique crystal structure, confirmed through diffraction patterns. From gemstones to industrial catalysts, knowing the structure helps us understand their behavior. Crystals are also central to quantum materials. In superconductors, electrons move without resistance through a crystal lattice, cooperating in pairs, called Cooper pairs. This phenomenon only emerges below a certain temperature and requires a crystal structure that supports the delicate quantum dance. In topological insulators, the crystal allows electrons to flow on the surface while blocking them in the interior. These exotic states matter are possible only because of precise atomic arrangements. Crystallography enables their discovery. It also plays a role in medicine. Drug molecules must fit into biological receptors, like keys into locks. Knowing the 3D shape of both helps chemists design more effective treatments. Many pharmaceutical breakthroughs depend on crystallizing a protein and studying its structure via diffraction. Crystallography has advanced through techniques like electron diffraction, neutron diffraction, and cryo-electron microscopy. Each method offers a different view, sensitive to different aspects of the atomic world. Cryo-EM, in particular, has revolutionized structural biology, allowing the imaging of large, complex molecules at near-atomic resolution. Beyond the laboratory, crystals fascinate us in daily life. Their geometric perfection, sparkling clarity, and symbolic meaning make them objects of beauty and belief. Yet behind every crystal lies science, precise arrangements, symmetry operations, and the deep language of structure. Crystallography also connects to group theory, a branch of mathematics that studies symmetry. There are exactly 230 space groups that describe all possible symmetries in three-dimensional crystals. Each space group defines how a unit cell can repeat and transform in space. These mathematical groups help classify crystals, predict new structures, and understand phase transitions. Phase transitions such as melting, freezing, or magnetizing often involve changes in symmetry. As temperature rises, a crystal may lose its structure, transitioning into a more disordered phase. Cooling reverses the process, but sometimes the system settles into a different crystal structure entirely. These transitions are critical in materials science, affecting everything from steel hardening to the behavior of shape memory alloys. In geology, crystals record the conditions of their formation. Minerals like zircon contain radioactive elements that decay over time. By studying these isotopes, scientists can date the age of rocks, sometimes billions of years old. In this way, crystals serve as time capsules preserving the history of Earth and the cosmos. Even ice cores from glaciers contain crystalline records of past temperatures and atmospheric gases. Reading these structures gives us insight into climate change and planetary evolution. Crystallography is not static, it's dynamic. New techniques let us watch how atoms move during reactions, capturing snapshots of chemistry in action. This field, called time-resolved crystallography, reveals the transition states that drive transformation. With ultra-fast X-rays, we can now watch electrons shift, bonds form, and molecules change shape in femtoseconds, a millionth of a billionth of a second. Crystals, once seen as rigid, now reveal motion at their heart. From the symmetry of snowflakes to the core of quantum materials, crystallography reveals that matter is not random, but governed by structure and repetition. Each lattice, each reflection, each diffraction spot is a signature of order, a fingerprint of the universe's architecture. It reminds us that beneath the apparent chaos of nature, there is geometry, there is symmetry, there is design. Chapter 23. The Deep Logic of Biological Systems. The body is not a machine, but a network of living circuits. Cells do not merely function, they calculate, adapt, and respond. Underneath flesh and bone, beneath heartbeat and breath, exists a world governed by feedback, signaling, and molecular logic. Biology, often thought of as messy, is built upon precise principles. It is more than survival. It is information processing on a living scale. From the blinking of an eye to the folding of a protein, biological systems obey rules as rigid as the laws of physics, only far more intricate. Take the cell life's basic unit. It is not just a bag of fluid, it is a factory, a sensor, a computer, and a replicator, all in one. Inside each human cell, tens of thousands of molecular machines are at work, transcribing DNA, translating RNA, transporting proteins, assembling membranes, digesting waste, and generating energy. These processes are not random. They are governed by reaction networks, with feedback, redundancy, and control. In engineering, feedback keeps a system stable. In biology, it does the same, only with enzymes, receptors, and gene regulation. For example, the lac operon in bacteria controls whether genes for lactose digestion are turned on. It functions like a logic gate. If lactose is present and glucose is low, the operon activates. If either condition is unmet, it stays off. This is computation, not in wires and silicon, but in molecules. The human immune system works the same way. It detects foreign molecules, classifies them, then launches a coordinated response. T cells identify infected cells. B cells produce antibodies. Helper cells regulate the timing, and memory cells store the result for future responses. These layers of logic are embedded in cellular receptors, protein cascades, and transcription factors. The body's homeostasis, its ability to maintain internal stability, depends on this precise network. Temperature, pH, glucose levels, water content, all are held within narrow bounds through continuous feedback. Even the heart's rhythm comes from electrical signals pulsing through pacemaker cells, a biological oscillator more precise than many clocks. The brain, too, is an example of deep biological logic. With about 86 billion neurons and trillions of synaptic connections, The brain processes more information than any supercomputer. Neurons fire based on thresholds, a form of binary logic. They integrate signals from multiple inputs, decide whether to fire, and pass the signal forward. This simple mechanism, repeated at scale, produces memory, language, sensation, and awareness. But the logic of the brain is not fixed like computer code. It rewires itself through experience, a phenomenon known as neuroplasticity. This adaptability is core to life. Organisms do not merely execute routines, they evolve, learn, and adapt. Even within a single generation, the body adapts to changing environments, regrowing blood vessels after injury, adjusting metabolic rates, or forming new neural connections. Biological logic is flexible. It can operate with noisy inputs, uncertain data, and partial information. This resilience is why life persists in deserts, oceans, radioactive waste, and even space. Consider the genetic code. DNA stores information using 4 bases: adenine, thymine, cytosine, and guanine. These bases form sequences, triplets called codons, that encode 20 amino acids. The mapping from codons to amino acids is redundant and error-tolerant. Some mutations change a base, but do not alter the final protein. This buffering against error is no accident. It is evolved logic, a system that ensures fidelity while allowing variation. Genes are not isolated commands, they are part of regulatory networks, genes turning other genes on or off. These networks function like logic circuits, switches, oscillators, and filters. Cells use them to decide when to divide, when to differentiate, and when to die. Apoptosis-programmed cell death is not failure. It is biological control. A cell with DNA damage will self-destruct to protect the larger organism. This is one layer of cancer prevention, a logic that prevents chaos in the system. But when that logic is broken, cells may grow unchecked, leading to disease. Understanding this network has led to targeted therapies, drugs that re-enable lost control pathways. Beyond individual cells, whole body systems follow similar logic. The endocrine system releases hormones based on internal sensors. The pancreas detects blood sugar and releases insulin. The hypothalamus regulates hunger, thirst, and body temperature. These signals are not linear, they are cyclical, rhythmic, adaptive. The circadian rhythm, our biological clock, coordinates behavior with the light-dark cycle. It is controlled by feedback loops in gene expression, synchronized by light-sensitive proteins in the eyes. Even plants follow this logic. They open and close stomata, track the sun, and grow toward light. In evolution, logic emerges at higher levels. Species interact in ecosystems through feedback and control. Predators limit prey. Prey abundance feeds predators. Plants provide oxygen. Animals produce carbon dioxide. This flow of energy and matter is governed by ecological logic. Food webs, nutrient cycles, symbiotic relationships all exhibit structure and resilience. When one species is removed, the effects ripple outward, a testament to the interconnected logic of life. On a molecular level, even folding is logical. Proteins begin as chains of amino acids, but they fold into specific 3D shapes based on interactions like hydrogen bonds, hydrophobic effects, and ionic forces. This shape determines function, and even small errors can cause dysfunction. Diseases like Alzheimer's and Parkinson's involve misfolded proteins. The logic of shape is central to biochemistry. In synthetic biology, scientists now design biological logic gates, circuits made from DNA and proteins that control cellular behavior. Cells can be engineered to detect toxins, produce medicines, or target cancer. These synthetic systems mimic the logic of nature while adding human intention. This is programming, but not in code. In molecules, bioinformatics reveals another layer. The genome is vast, but by using algorithms we can find patterns, motifs, repeats, signals, and structure. Genes are annotated, networks are modeled, mutations are tracked. We now understand evolution not just as descent with modification, but as a shifting landscape of fitness. Proteins and traits evolve through small logical steps, mutations that alter structure or function. Some confer advantage, others fade into noise. Biological logic includes randomness, but is shaped by selection. From enzymes to ecosystems, from bacteria to brains, life is logical, layered, and adaptable. It operates on physical laws, but organizes them into living patterns. There is beauty in this logic, not just in what it does, but in how it evolves. No designer planned it, but over billions of years, trial and error sculpted rules. These rules persist because they work, and as we decode them, we glimpse how life truly functions. Chapter 24: Quantum Biology, Life at the Edge of the Unseen. Life, for all its complexity, has always seemed to belong to the warm, messy world of chemistry. Molecules reacting, cells growing, tissues forming. But deep within this realm of biology lies a subtle undercurrent, an invisible quantum dimension where particles behave in ways that defy intuition. This is the field of quantum biology, a young, surprising domain where the rules of quantum physics seem to shape the very core of life. At first glance, it seems impossible. Quantum effects like superposition, entanglement, and tunneling are fragile. They vanish quickly in warm, wet environments like the inside of a living cell. And yet, evidence keeps emerging in processes as fundamental as photosynthesis, bird navigation, smell, and even DNA repair. Quantum effects may not only exist, they may be essential. Start with photosynthesis. It's one of the oldest and most vital biological processes. Light hits a leaf, energy is captured and turned into sugar. But how does the plant efficiently transfer that light energy through a dense web of proteins to reach the reaction center where it is used? In 2007, researchers used ultrafast lasers to study the energy transfer in photosynthetic complexes. They discovered something unexpected. Instead of hopping randomly from molecule to molecule, the energy appeared to explore multiple paths at once, as if it was taking every possible route and then choosing the most efficient one. This is quantum coherence, a phenomenon where particles like photons exist in a superposition of states, exploring many trajectories simultaneously. It suggested that photosynthesis might exploit a quantum search algorithm to transfer energy with near-perfect efficiency. If true, this would mean that evolution has somehow harnessed quantum computation inside a living cell. Another mystery is how birds navigate. Some species like the European robin can migrate thousands of kilometers with astonishing accuracy. They appear to use Earth's magnetic field as a compass. But magnetic fields are incredibly weak. Too weak, it seems, to influence molecules through classical physics. Enter the radical pair mechanism. Inside bird retinas, a protein called cryptochrome forms pairs of electrons whose spins are quantum entangled. This entanglement, a non-local connection between particles, may allow birds to sense direction based on how the entangled spins evolve in Earth's magnetic field. If correct, this would be a rare case where a biological system maintains quantum coherence long enough to be useful, even at body temperature. Quantum tunneling is another possibility. In classical physics, a particle cannot cross a barrier unless it has enough energy, but in quantum physics a particle can tunnel through the barrier, appearing on the other side without crossing it in the classical sense. There's evidence this may occur in enzyme catalysis. Enzymes speed up reactions sometimes by factors of 1,000,000. They do this by stabilizing transition states and reducing energy barriers. But in some cases, the reaction proceeds faster than expected. Proton or electron tunneling could explain this. Rather than climbing over the barrier, the particle tunnels through. This would make certain biochemical reactions depend on quantum probability. Even olfaction, the sense of smell, has been suggested to involve quantum effects. The traditional view holds that odor molecules fit into receptors like keys in locks, but this model struggles to explain how we can distinguish between molecules that are structurally similar but smell completely different. In the vibrational theory of smell, receptors may detect molecular vibrations via inelastic electron tunneling. This means the receptor could listen to the frequency of the molecule's bond vibrations, a quantum fingerprint of smell. While still debated, experiments in fruit flies and humans show hints that this theory may hold some truth. Another area of intrigue is mutation and DNA repair. Mutations often involve the mispairing of bases in the DNA ladder, a G where there should be an A, for example. Some researchers propose that protons in the hydrogen bonds between bases may quantum tunnel from one side to the other, creating temporary mismatches. If the replication machinery encounters this state, it might copy the wrong base, leading to a mutation. Conversely, some enzymes that repair DNA might use quantum effects to detect and correct errors based on energy resonance or wave-like behavior. None of these examples prove that life uses quantum physics in the same way a computer might, but they suggest that at the smallest scales, quantum mechanics may not just be noise, it may be essential. In quantum biology, the challenge is evidence. Quantum phenomena are fleeting. Measuring them in cells is extremely difficult. Coherence, entanglement, and tunneling are well documented in physics labs, usually under extreme cold and isolation. But living cells are hot, wet, and noisy. The assumption has long been that quantum effects are quickly destroyed in such environments. Yet certain biological structures may protect coherence. Proteins may form quantum cages, limiting interference. Some molecular networks may act as quantum wires. Vibrational modes in enzymes might synchronize electron movement in a way that preserves entanglement. This is speculative, but research is advancing. In artificial systems, scientists have mimicked photosynthetic complexes and observed quantum coherence at room temperature. They build quantum simulators to test hypotheses about biology. If coherence can persist in these analogs, perhaps nature found a way to do the same. Quantum biology is not science fiction. It is rigorous, cautious science at the intersection of physics and life. It asks, is the weirdness of the quantum world just a foundation beneath life? Or is it a partner in life's evolution? Could evolution have selected for molecules that use quantum rules for advantage? For faster reactions, better sensors, more efficient energy transfer? If so, life is not merely classical. It is quantum enhanced. And if life can evolve to use quantum mechanics, what else might it evolve to understand? Could the brain host quantum processes? Some theorists controversially propose that consciousness might involve quantum states in microtubules within neurons. This idea, known as ORCHE or orchestrated objective reduction, remains debated and unproven, but it points to the larger possibility that the line between physics and biology is thinner than we imagined. Life is not separate from the universe, it is an emergent property of it. If quantum mechanics governs everything from stars to atoms, then life too must obey and perhaps embrace it. Perhaps quantum effects do not violate biology. Perhaps they enable it. In the future we may engineer molecules that perform quantum logic in cells. We may design synthetic life that runs on entanglement tunneling. We may even discover organisms on other planets whose biology is even more deeply quantum. The more we study quantum biology, the more we are reminded life is not just complex, it is subtle. It balances between determinism and probability, between matter and information, between noise and coherence. To live is to compute, to sense, to adapt. Sometimes perhaps with the help of a universe that allows particles to be in two places at once. Chapter 25. Emergence. When simple rules create complex universes, how can the fluttering of a bird's wing, the growth of a forest, or the workings of your mind, all arise from particles that follow simple laws? This question brings us to one of science's most profound frontiers, emergence. Emergence is the phenomenon where larger patterns, behaviors, or systems arise from the interaction of smaller, simpler parts, not through design, but through process. A single ant is simple. A colony of ants can solve complex problems like building bridges, regulating population, or finding the shortest path to food. No leader commands them. Their behavior emerges from local rules and interactions. A water molecule is just hydrogen and oxygen, but trillions together flow, form waves, create pressure, and shape weather. Your neurons are cells. Each obeys chemical rules, but together they form thoughts, emotions, creativity, and awareness. These are not metaphors, they are scientific examples of how systems self-organize, scale, and evolve complexity from simple interactions. In physics, emergence explains how temperature, pressure, and entropy arise in gases. No single molecule has a temperature, but collectively, billions of them moving together create heat. In biology, emergence defines how organs develop from tissues, how ecosystems stabilize, and how flocks of birds move as if sharing a single mind. Emergence is not magic, it is pattern, and it often follows mathematical rules. Consider cellular automata, mathematical grids where each square updates its state based on simple rules applied to its neighbors. The most famous example is Conway's game of life. On a simple grid, cells turn on or off, depending on how many neighboring cells are alive. From these basic rules, complex structures emerge. Some static, some repeating, some traveling across the grid like living organisms. Some patterns even behave like logic gates, suggesting that computation itself can emerge from pure rules. This echoes a deep truth: the universe may be built on simple laws, but the outcome is complexity beyond prediction. In nature, emergence appears in fractals. Fractals are self-similar structures that look the same at different scales. Coastlines, snowflakes, and Romanesco broccoli all exhibit fractal geometry. They form through recursive growth, where each small part copies the whole. These patterns arise from feedback loops, alliteration, and physical constraints, not from top-down design. In chemistry, self-assembly is a form of emergence. Molecules in a solution spontaneously form membranes, micelles, or crystals, based on shape and charge. Life may have begun this way, with simple lipids, self-organizing into protocells in the ancient oceans. Even consciousness, the most mysterious property of the brain, may be emergent. No single neuron feels pain or joy, but the pattern of neural activity creates the subjective experience of being. Some neuroscientists propose that consciousness arises from integrated information, a measure of how much a system's parts affect each other. This theory, known as integrated information theory, suggests that beyond a certain threshold of complexity and integration, a system begins to experience. It's controversial, but it offers a scientific framework for the emergence of awareness. In complexity science, emergence is studied using models of networks. Nodes represent elements, edges represent connections, and the behavior of the whole depends on how the parts interact. This approach applies to brains, cities, economies, and the internet. Each exhibits resilience, adaptability, and phase transitions, despite having no central control. Phase transitions are a classic example of emergence. When water freezes or boils, it changes its properties suddenly. At a critical point, the gear of the system can shift dramatically from fluid to solid, or from disorder to order. In social systems, this might look like a viral meme, a sudden stock market crash, or the tipping point of social change, all governed not by one cause, but by the build-up of small interactions, crossing a hidden threshold. Emergence is also visible in evolution. Genes mutate randomly, but over time, selection and feedback produce complexity. Wings, eyes, language, and cooperation all emerged from the simple logic of variation and survival. There was no blueprint, only possibility, filtered by environment and time. Even in physics, emergence bridges the quantum and classical worlds. Particles behave probabilistically, but at large scales, matter appears solid, predictable, and classical. The familiar world of cause and effect emerges from the strange rules of the quantum realm. Scientists are now exploring whether space-time itself is emergent. Some theories suggest that gravity, space, and time are not fundamental, but arise from deeper networks of quantum information. In this view, the universe is not built from particles, but from bits of correlation, and geometry itself is a large-scale illusion. Emergence explains not only how things form, but how function appears. A single neuron doesn't think, a single bee doesn't plan, but collectively, they form systems with memory, strategy, and decision-making. In artificial intelligence, neural networks learn by adjusting weights between simple nodes. No single node holds the solution, but the pattern of interactions does. When AI learns to translate, recognize images, or mimic speech, it does so through emergent behavior, a cascade of local adjustments producing global intelligence. As our tools for modeling and computation grow, we may uncover new layers of emergence within matter, energy, and thought. But perhaps the most profound truth about emergence is that it reminds us of humility, that from the simplest beginnings, from randomness and rule, can come beauty, meaning, and awareness. That life need not be imposed from above, but can rise from the bottom, unexpected, undesigned, and unstoppable. From ants to galaxies, from neurons to consciousness, from atoms to space-time, the universe is a poem written by interaction. A single rule, repeated, becomes a dance. A single feedback loop becomes life. And in this dance, we are both the product and the process, emergent, aware, and ever-evolving.